who should do? It's not yet very legal. Yeah. That's what I'm looking at. We're looking for the section. I mean, it's just between two of us, we thought, okay, GitHub is good. But if we have a solution for some other.
Oh, yeah, yeah. Yeah, it's key there. Yeah.
The boards for Android. Proceed from there because the website is staying on the other page. You don't know what that. So there's domain, but no content, no. It's just that when you thought of the project, you just took the domain at that time. And that is still with us if you want to explore that option.
Is this mic live too?
I mean, I have to check, but I think
This is good? Okay. Second mic. Well, we do have a queue, but I also just want to have something.
okay.
Oh, right, on the other side. I'm going to see if you can do that. I know the screen is pretty small, but the fonts are very small. So way back, if you are joining with the big blue button on your own laptop, just make sure you don't connect to either the audio or the mic if you're in the room. And so when it prompts you for that, just hit the X and quit out. That's good. And then this one, do I need to tap? Okay. Yeah, perfect. Well, I was going to grab it and go around, yeah. All righty. Hey, everybody. Thanks so much for joining us at the Android Micro Conference at Linux Plumbers. I do want to say thank you first to the sponsors who, we would not be able to have this without them. So thank you very much. Also, just want to remind everyone we have a code of conduct, and so the idea is that discussions can be vigorous, but they need to be civil. So please keep to that. And with that, I'm going to kind of kick right into the first speaker here. And so let me see, what is going on with the thing? Oh, there we are. Alrighty. With that, I want to introduce Todd and speak on Android device longevity.
Hi there, I'm Todd Chose from the Android kernel team. And, okay, how do I advance it?
Arrows at the bottom there. So get to that, and then just click.
Okay, enter, okay. Okay, so first we're gonna do a little history of the Android common kernel. Back in 2016 and before, the Android common kernels, which we created from the upstream LTSs, were basically patch repositories. Nobody actually used them in production. We didn't actually do a lot of testing with it. What happened back then was that the common kernel was cloned by a silicon, one of the silicon providers, and they added all their stuff to it, and then they passed it on to their customers, the OEMs, who added their stuff to it, and in the end, we had kernels out there, kind of an individual customized kernel for just about every device. We started to have stronger opinions in 2017, and especially we were looking at security issues at the time, and so we worked with upstream maintainers, in particular Greg, and got the upstream lifetime of the kernels, the support lifetimes extended to 6 years, starting with 4.4. And we started internally doing LTS updates, and the first one was Pixel in 2017. And we observed that when security issues came in and reported to our security team and reported in our Android security bulletin, that 93% of those things, exploits that were out there in the Android community, 93% had already been fixed on Pixel by taking LTSs and keeping it up to date with the LTSs. And phones, of course, are very attractive targets because you have a lot of personal information, and so we decided that we need to take a very proactive approach and not wait for exploits to happen on Android, and instead get in front of them by merging LTSs. So then we started requiring LTS updates, starting with 5.4 for everybody in the industry, and that was quite painful because every phone had its own individual kernel. And so that was one of the precursors to what we do now, which is GKI, where we actually ship a binary, where we do all of that work to do the LTS updates, to track the stable kernels, and our partners just take that binary, they do their own testing with their drivers, and ship the binary as is. So the ACK is now, it is product. We do a lot of testing. Our partners do a lot of testing with it. So you have well-tested kernels that are tracking upstream. Uh-oh, now what happened? No, it's still there. What? Okay, well, okay. Is that all right? Okay, that's good. I'll call you back up in a minute or two. Okay, so the lifetime that we had with the 6-year upstream lifetime was that we would create our ACK kernel shortly after the upstream kernel was. So in my example here, 4.14 was created in 2017. And then the silicon vendors immediately take that, do their work, and then they typically have the first release late that year, and then the next year the silicon never had to change kernel major version. It would stay on that same 4.14 kernel. They would do their premium devices the first year, and then they would do mid-range devices and low-end devices and other derivatives the following years. And then after the third year, they would have new launches, and then those devices would have, say, a 3.5 year lifetime, and then they would be end of life, and all of that fit within that 6 years. So it kind of worked. That's kind of how we got to the 6 year, and it kind of worked. And now the scary part, I'm going to try to go to another slide. Okay, so I'll just keep talking, and we'll see if we get more slides. So what was observed, however, by the upstream maintainers was that there was zero engagement on these old kernels after a few years. So for years 5 and 6 in particular, there was no upstream folks doing any testing. There wasn't the stable kernels weren't getting much testing. Even in the Android community, where those devices were out there in production, nobody was paying attention. Nobody was reporting issues back to stable. And so the upstream maintainers, Greg and Sasha and others, said, look, this isn't working. We're kidding ourselves. We're not really getting the protection against exploits and so on these really old kernels, so we're not going to maintain them so long. And so if you look at kernel.org now, and what's circled on the slide is that 5.15 is going to have a 5-year lifetime, 6.1 is down to 4 years, and 6.6 is 3 years. And so the whole way that the Android ecosystem worked kind of gets broken by that. And you'll notice on the far right column, this is all public now. We publish the end of life dates. We didn't used to do that. We recently started. So you can find this online. But since we promised our partners that 5.15 and 6.1 would be 6 years, we are going to keep it alive and do our best. But it's, same comment. It really is, we're fooling ourselves a bit by thinking we can do a great job of that. But we are going to support those for 6 years. And,
Try using the side arrow.
This one? Okay. Okay, so the way things are now is with the 6.12 kernel, it's going to have a 4-year lifetime by Android, so we don't know yet exactly what the upstream is going to be, but Greg is working with us to at least keep it for 4 years. And so we'll have device launches, and that first device that launches can do upgrade, and if it was going to stay with the old cadence of a 3-year lifetime, then that works, but only for that first year. And of course, Qualcomm and the other silicon vendors want to keep launching devices with their silicon and make money on it. So something's got to give, because we're going to hit the kernel end of lives before device end of lives. And kind of to make it even more complex, you have things like the EU Eco-Design Directive, which says that you have to keep giving feature and security updates for 5 years after you're no longer sending it out into the channel. And so devices are definitely going to be lasting a lot longer than the kernel lifetime. And so what now is going to be happening, and is sort of the next evolution of the Android Common Kernel, is that devices are going to be updated with new major kernel versions in the field as part of OTAs. And so we're gearing up, we're doing a lot of work to make that smoother and working with our industry partners, because it's a big change, especially for OEMs who often have been used to kind of shipping it and never thinking about it again, now having to do some real engineering on these devices that they don't make that much money on. So there's some big ecosystem problems that we're working through with folks right now. But what we're not doing is we're not letting them run with end-of-life kernels, because we consider those guaranteed to be vulnerable, because nobody's looking at them, nobody's paying bounty hunters to find issues. So only the bad guys are looking at those and trying to find stuff. So one of the other things we're doing now is we're starting to enforce end of life. So when partners want to upgrade the security to get a new security patch level so that they can show their users that they're maintaining their device. If they're running an end-of-life kernel, the test that validates that you're secure, the STS test, will fail, and the SPL cannot advance. And so we're forcing the hand that their hand to have to do uprevs. One thing that's nice from an ecosystem point of view with that is, for the first time, really, our partners, our silicon partners and OEMs have a strong incentive to upstream things, because now they're going to have to go back and get their drivers, get their product working on a newer kernel version. They can't just abandon the old one and go on to the new one for their new silicon. They have to actually support their old silicon on the new kernels along with their new devices. So we think GKI helps with that, because at the abstract level, all they're doing is going from one GKI kernel to another GKI kernel. That should work. It's all supported. And the complexity then is their drivers, the drivers that implement the SoC features and the drivers from the OEMs that implement the board features. That's where all the complexity in this is. And so if they have their drivers upstream, they get a lot for free. They don't get the performance and power tuning for free, but they get at least a lot of the maintenance for free. And if they're tracking mainline with their devices, they get a lot of that easier. And so this is kind of a function to help incent them to upstream their drivers so that we have fewer and fewer out-of-tree drivers. That's one of the dynamics we're going to see, but we're not going to completely get rid of out-of-tree drivers. In fact, I think we'll still be dominated by out-of-tree drivers for a lot of the silicon. So we do have a bunch of support, a DDK, to help with that as well, to make it easy to switch between kernel versions with your drivers. You can maintain a driver, you can compile it against multiple upstream kernels and deal with the portability things. And then, of course, they still have to deal with the power and performance tuning. The other thing that we're doing is, so we have a few of our partners who've already done this a couple of times, and they've reported regressions for some Android workloads that they care about as they go from, say, 4.19 to 6.1 kernels. And we were not doing a good job of tracking regressions. We were doing a lot of work within a kernel branch, but we weren't really looking at regressions from one branch to a newer branch. And so we've started doing that and encouraging our partners to do the same. And so we're trying to get a lot of help in place to make this as smooth a process as possible, but our partners are going to have to do uprevs of the kernel version in the field. So I don't know how much time I have for discussion, but Okay, good. So I wanted to throw the discussion open of what, for those of you who are going to be dealing with this, if you have devices out there, what is scary to you about this, and what can we do to help, and what would you like to see? We have, it's really starting with next year's devices, because they're going to have the shorter kernel lifetime. So the devices that ship next year are probably going to need an uprev in 2 or 3 years. So there's a little bit of a runway to do stuff. Questions, comments?
Yeah. Obviously, from my perspective, I work at the Amazon Devices Organization, and from my perspective, it's all of the extra drivers that the SoC vendors are adding. I'm not so concerned about the kind of the code they add into the GKI hooks, but we get a steaming pile of ABI of binary drivers from those SoC vendors. How are we going to work with those SoC vendors to make sure those drivers get ABI updated to the new kernels? And how are we going to actually get them to do any validation when they make $0 off of that work?
Yeah, so that's where we've been spending a lot of our time, is talking to at least the major SoC vendors. and dealing with that question. So for most of them, I can't talk about precisely what each of them are doing because they all take slightly different approaches. But the general idea is that they're going to update their BSP probably on a 2 or 3 year cadence, so that you, as a customer of an SoC vendor, you'll see them come out, and you can ask them the question because they should be able to talk to you about it now. But you'll see from them an updated BSP that goes from, say, 6.6 to 6.18 or whatever after about 2 or 3 years, and they can probably give you the date of when that will happen. So then you, as a OEM or as the next level on the chain, you should have a completely validated, tested BSP that you can then take your drivers and rebase them to the new kernel target.
And the other question is AOSP versus Android. Is this all Android work, or is this also falling back into AOSP?
So this is this is really not it's AOSP in the sense that we publish our kernels in AOSP, but what you're really seeing happening is we still have our 6.6 kernel there, and there'll be a 6.18 kernel there, and you will be moving from that 6.6 kernel to the 6.18 kernel. That's an AOSP. And then, you know, our silicon partners who is your vendor, they're using that. They're using AOSP based, you know, those AOSP based kernels and platform code to give you what you need. So I think we've covered your case, but you need to talk to the silicon vendor. And then if you have concerns and questions, did I put? Let me see if I put. No, I didn't. Okay. So you can, if you have a relationship with Google and can file bugs, you can file a bug. But you can also, we have an email alias, kernel-team@android.com. And if you have concerns or questions or ways that you think that your silicon vendor isn't supporting what you need to make this happen, then you can hit us with that email.
You're talking about getting vendors to move to newer kernels on their devices, but you're not doing that yourself. I have a Pixel 7 in my hand. I bought it 534 days ago. It's still running a 5.10 kernel. So why?
So it's really starting. So we first announced 7-year support with Pixel 8. So if you have an older Pixel, it's not in this new regime yet. Pixel 8 is. Pixel 9 is. And so we are doing it ourselves, but we're not going back and doing it with the older devices. Other questions, concerns? Okay.
Thank you so much. For some reason, when you do this, it was pasting, like just junk. And so, I think maybe click once there, and then afterwards just use the arrows. Yeah, okay. Yeah, okay.
Lucas, can you hear us?
I don't think we can hear you. You're on mute still.
Does it work now?
Yeah, we can hear you. You're loud, though.
Yeah, you're very loud.
Okay. I can pull it down. Now better? Is it better now? Hello? I don't hear you now.
Yep.
Hi. Yeah. Perfect. So I'm Șerban Constantinescu. I used to be a Googler, working very closely with Todd and the rest of the team on longevity. And I've recently left to start Source Dev with David, also ex-Googler, partner in crime, working on making some of the tools that you would need to support software for longer. Together with my colleague, Luca Weiss from Fairphone, we're going to talk through some of the other problems that you would have with device longevity besides the kernel and the work that Todd talked about. So first of all, just two aspects on longevity. As you've seen from the audience, longevity is not just something that regulators want. It's actually something that users want. And there's a yearly GSMA survey. And you could see that in 2023, the top drivers for purchasing the next smartphone were actually longevity related. You can find the slides online and take a look at what the survey says. But users do buy longevity. And we're actually seeing that this is the case not just for smartphones. People do the same when they look at cars, and probably they're going to do the same when they look at TVs and other form factors. Second, regulators are actually planning on enforcing long-term software security for devices. It's not just smartphones and tablets. That's what they're starting with. EU eco-design that Todd mentioned comes into effect 20th of June next year. But there's regulation that covers IoT. There's regulation that covers automotive. There's regulation that covers medical devices. And all of those countries that you see there are working to some degree on their own regulation, much of which we're hoping to standardize. So we're also working closely with them on educating and trying to make sure that that regulation is not just going to fragment your work further. But on a whole, regulation says that devices should be supported for more than 5 years. In the smartphone space, this could actually end up being 7 years if you sell a device for 2 years. These devices should get timely security updates. So within 4 months of public disclosure of a vulnerability, that vulnerability should be fixed in field. They should get frequent OS upgrades for EU eco-design. That's 6 months after some sort of release of a new operating system. You should apply that. There should be a comprehensive understanding of the supply chain and what gets integrated in that device. And there's also talk of a standardized vulnerability management system. If you look at this, even in the smartphone space, it's actually quite fragmented. I think Google and Pixel and Samsung and probably Apple are state of the art in terms of vulnerability reporting. So we at Google worked on this for over 2 years. But we also talked with a lot of you folks. We've done surveys. We've done a live stream that's linked there. We've done one-to-one conversations. And these are some of the issues that are top of mind for you. And the rest of the session is mostly a Q&A, trying to look at how we can resolve some of those issues. So the first one is we've already discussed, is that there are a lot of binary-only BSPs, and also a lot of the modifications that are done with AOSP are probably not done with longevity in mind. I think as we get code generation tools, there's surveys out there that say that the quality of that code that gets generated is actually poorer than it used to be before. So I think it's very important not to end up with this rotten Android, and we should think about it from the get-go. There are many interfaces that Android provides. Treble has obviously been there for ages. It's actually tremendously helpful, but there's still many devices out there, maybe outside of the smartphone space, that don't use this. So we should probably start with that. We should also probably take a look more closely at the vendor interface. And actually, if you attended Chris Simmons' talk on the build systems, on the Android build system, one of the questions that came up there is, how should we maintain devices for long term? This is an interface that is probably now, is it 4 years old, vendor interface? Yeah, okay, more than that. So basically what the vendor interface says is that there's a decoupling between the BSP and the upper layer of the operating system, and that Google takes on the compatibility management. So if you have a vendor interface that's, say, Android 14, then Google would cover 4 years and maybe looking at extending that. So you should definitely take a look at the SoCs that have that. Any other thoughts on how we could tackle these problems? Or to Todd's point, maybe some of the tools that are missing?
So one way to tackle this better would be to have vendors push everything upstream. Obviously, not everyone's going to do that, and for not every component. But over time, I think it would make sense to try and reduce the size of these BSPs, and I think that makes maintenance easier for the SoC developers, it makes maintenance easier for the OEMs and the operating system distributors. So it's something I'm always harassing Todd about, as the Chrome OS team moves into Android, this is something that we're going to be pushing on as well. And of course, our model is kind of weird because we're going to be acting as the OS distributor and maintainer rather than the OEMs. And so we're going to be really affected by this. So I'm definitely pushing vendors to push things upstream to save trouble. I do worry about, major Android version upgrades and having a BSP that's old, compatible, but old, and thus missing support for maybe new HAL extensions or something like that. I do worry about getting stuck in that situation, but I don't know if people have good answers on how to address that. But.
Yeah, I think that's a very good point. I have a Pixel 8 Pro that I probably worked on while I was at Google. It runs approximately 120 million lines of code in pretty much every programming language that you can think of. If you extrapolate forward what a Pixel 5 would have had if it was to be supported up until today, 50% of the code that would be running today on that device would be new code that that device didn't originally ship with. So to your point, I think the more of this code is upstream, right, the more you, the lesser you pay on that maintenance tax. And really the call to action here is think more about that and let's help each other figure out what tools are missing or what practices are missing to be able to do that. Just in the interest of time, I'll move on to the next slide. And Luca, please feel free to jump in. Okay, the other obvious thing is the regulation, at least for smartphones, says that you should be updating, fixing security patches within 4 months, or upgrades within 6 months. That's probably not going to apply everywhere, but a lot of the IoT regulation that's coming in 2026, 2027 is probably going to inherit at least the security timelines here. So really the model we have today with multiple development branches doesn't really scale. Actually, even at Google, Android is moving to a new development model called trunk stable. It used to be that the months of January, February, and March, we would get really buggy dog food devices because we would try to stabilize the code base. And really, the way to maybe deal with some of that is to move to this new development model where actually you have one branch where you use flagging, where you use the Android tools that exist, and develop things behind flags rather than have multiple branches for supporting each one of those. And that could ease some of the testing cost, could ease some of the security patching costs, and could actually enable you to go faster to the next OS upgrade. So yeah, there's probably, I think at scale, there are very few people that actually track, very few companies that actually track what's happening in Android to very granular basis. Very few people that probably track what's happening with the work that Greg and Todd are doing with the Android kernels. And maybe that's a way to actually detect issues earlier when they come in and go and work with the teams upstream on fixing those. So really, we think that there's a lot of DevOps that's missing here, and then that this might actually help you. Any other thoughts on how we could better deal with this, or like what's some of the tooling that's missing?
I think one thing I was also mentioning before was that basically trunk stable also needs support from the SoC vendor. So if the SoC vendor only gives a certain Android version, then also the OEM is kind of stuck on the version that the SoC vendor provides. So it needs support from both sides really, like both the OEMs updating to the new version from the suppliers and the supplier actually updating it.
I do realize that I haven't properly introduced Luca. For those of you that don't know, Fairphone is probably the company out there that supports the longest lasting Android devices to date. And they really last for a long time. It's not just the software, actually the hardware. We're talking primarily about the software here, but the hardware is also a big component to being able to last so long. And actually a lot of the regulation is also talking about hardware cycles and improvements there as well. Okay. So another fun fact about my Pixel 8 is that it also incorporates 20 or 30 other providers. And this is just like a generic number. You've seen some of the supply chain attacks, but actually the supply chain for smartphones or cars, it's actually quite complex. You don't end up just working with the SoC and the OEM and the ODM. There are probably 20 or 30 other companies that you need to work with that do anything from the fingerprint provider to the audio chip to maybe something small on the side, maybe the camera hull, maybe the camera framework. So you should, I think, those are also folks and companies that need to think about long-term software support, because updating the devices would also involve work that needs to happen at their end, at least testing that needs to happen at their end. I think I've heard of an example where the device was supported for a long time, but the NFC chip wasn't, and there were all sorts of issues with that, especially when moving forward to Android releases. There are all sorts of other problems like that. So it's not just the folks in this room that need to think about this, it's also the folks that you folks work with that probably need to think about this. And again, I think the only silver bullet there is just to figure out the way to more continuously track this upstream changes on a more granular basis than they do today, just so that when issues get introduced, issues get detected and probably fixed to some degree. Luca, anything to add here?
I think not. Maybe from the audience?
Anyone else in the audience that has any particular war story to share here, or tool that magically saved them, or any other thing?
Hi. I just want to bring up one other thing, which is automotive, which is going to compound this problem by several factors. So automotive hardware is in the market for 10 years or more. So what are you going to do when you need a 12-year, an 18-year support cycle? It's a problem that we all have, but it's a problem that has to be solved somehow. Otherwise, we can have people driving around in buggy cars, and we don't want that.
And the only thing I'll add to that is what Todd said at the beginning, like you should bear in mind that many of these risks are not just theoretical. They do happen, and they do happen at scale. and they will continue to happen if we don't fix these devices and keep them updated. Any other thoughts?
I guess probably everyone in this room is aware of it, but I have the urgent request that all the device makers at least make the source for their drivers and firmware and things available. I've been trying to keep a Nexus 6P alive for about 12 years. The hardware survived it, and I could update it to newer Android releases even, but at some point it became impossible to keep a couple of stupid binary blobs going, at which point the device became worthless. So it should really be a requirement that at least the key drivers and things are open sourced, or at least in a source available license so people can port them to newer releases as needed.
Yeah. My product manager hat on now. I think this is to a large scale a supply and demand problem. Today there doesn't exist a lot of supply for a lot of demand for software updates besides folks like Fairphone and many others of you here. But the regulation is going to encourage that, and I do hope that people are going to be more upstream friendly as a result of that.
Just a plug, kind of related, I don't know if everyone's aware of it, but the firmware update project has been a pretty good success story. And it's not really in the Android ecosystem yet. I'm hoping we can push it in, but that's a place where vendors have been pretty willing to work on adding what's necessary for getting their device firmwares updated by the system. So if you haven't checked it out, check it out. It's a good thing.
Just in the interest of time, I'll move on to this last slide. So there's a lot of regulation that's coming. Don't think that the regulation is not going to impact your devices if they're internet connected. If they are internet connected, they will be impacted sooner or later. UK PSTI is already into effect. If you look at, you could ask me after the meeting, and I could show you how bad that looks. But yeah, in terms of like not the requirements, but in terms of like the software supply chain where it is today, EU eco design is coming into effect 20th of June next year, and there's a lot of laws coming up, primarily from the European Union and others on this topic. And yeah, you should probably consider maybe reading those regulations or thinking a little bit about it. There's a cheat sheet here at the end. I don't expect you to be able to read this, but this is like some of the regulation that you should have in mind, and some of the wording in there, and some of the impact. As Chris said, there are actually form factors where the support required by some of this regulation is going to be vastly exceeding those 5-year mark. For example, for maybe cars are a good example, where the regulation says that you provide software updates for the intended lifetime of that device. So yeah, please ask me or some of my colleagues or Todd or some of the other folks that are thinking about this if you need any help. Thank you.
I also want to mention that Karim from Opus has been very important in getting this all set up and especially running the live stream.
Can I use this microphone? Okay, I'll use this one. Okay, so next topic. I want to talk about communities. Yeah. So, statement of the problem. AOSP is used in many different types of devices, some of which we have mentioned. Most of these groups rather, are developing their own customized versions of AOSP. Some of them licensing from Google, some of them not. So consequently, we know for sure there's a large group of developers out there working on AOSP. So I did a rough calculation about this. It's somewhere between tens of thousands to hundreds of thousands. So it's not a small group of people. But where are they? It's like the Fermi paradox, but for software engineers. Fermi paradox, ask me later. Contrast this with other open source projects that do similar things. So I'm picking on Yocto project here as being a good counterexample. Yocto does essentially the same as what AOSP does, but in a different way. So they have a vibrant and open community. So essentially, I'd like to have the same, please. Community then is more than just free code. It's not a free download. It is sharing, communicating, contributing. That's what I mean. So to elaborate that a little bit then, the problem is the way that AOSP developers work. Everyone is an island. Everyone's working together, working alone on their problem, or in small teams or whatever. Little communication between teams, even in the same company, they frequently don't. Little opportunity to get together with others. Little sense of there being a community at all. So everybody's on their little island. They don't see the other islands around. Even with a telescope, you still can't see the islands across the sea. Just drilling down a little bit on this community thing. Community means sharing information. It's not just downloading stuff to get the maximum benefit out of open source. It's about sharing. It's about asking questions, replying to questions, sharing useful information, and all those things. So I guess you could ask then, why hasn't this happened? If this is such a great idea, why don't we just do it? And I've come to realize that community isn't necessarily something which just happens organically. It needs something, it needs some focus. It needs some kind of leadership to coordinate and promote all this stuff. Why is community a good idea? I've said some of these things already, but I want to focus on the win-win part of this, just to emphasize that community is not a threat to OEMs. So community works, the idea of sharing works both for the individual, because you get to share stuff, you get to recognition within the community, which is a nice thing. We all like to get recognition. It works within the team, because you get, if you're a product manager or a product owner, you get benefit of scale, you get benefit of people becoming better at their jobs. We talked about upstreaming just now. The more of this stuff that can be upstream, the better. And again, don't be afraid of upstreaming. Upstreaming is a good idea. Just do more of it. And you know who I'm talking about here. And then at the company level, again, open source is not a threat. It is not stealing your intellectual property, because this is all open source anyhow. It is reducing your exposure to open source by sharing it and sharing the maintenance of all of that. So this is all good stuff, and just a note at the bottom there, I'm talking to you, Google. This applies to you as much as anyone else. So contrast this then with Yocto. So I happen to work quite a lot with Yocto people. I know the Yocto project pretty well. And like I say, fundamentally, Yocto does the same thing as AOSP. How do they do it? Well, it's quite a small community, I should say. There's not a particularly huge number of people there, but they have mail lists. They have people answering those mail lists. If you ask a question on the one of the Yocto mail lists, you'll get a response usually within 24 hours, quite often less than that. They are open to patches. We can send patches to the Open Embedded and Yocto people, and they will be very receptive to that. They have Dev Day conferences. They had one yesterday, in fact, in this very building. They have advocates for the community. In particular, I'm talking about Josef Holzmeier, who I'm sure you all know. He does a tremendously good job at promoting the Yocto community. And they are set up. They have an open decision-making process. They have a technical steering committee. All this stuff is made public. So the whole thing is done in the open. Everybody has a part of this. What do we have? So right now, well, from Google, what did Google give us? Not a lot. We have some Google groups, but nobody ever answers any of the mails there. They are basically useless. What about the organic community? So there's a bunch of stuff on Stack Overflow. Quite often when I'm trying to solve a problem to something, I'll Google it and I'll search for it, and it will point me to Stack Overflow. Some of the information in there is good, some of it is not so good. We have a meetup. So I myself run a meetup every 2 months, and that is a means which is somewhat successful to get people to talk together. We have the AOSP developers community, which I think was started by John Stoltz and a bunch of others, and a bunch of people here from Bay Libre and from Linaro and many other places use that as a means of communication. Cool. We have various podcasts. I'm looking at the ADB, the Android Developers Backstage, Chet Haas, and a bunch of other people now. Not specifically AOSP, although they frequently impinge on AOSP-type topics. And we have occasional ad hoc meetings at various conferences, including Plumbers, as we are here right now, but also at the Embedded Linux Conference, Linaro Connect, DroidCon, particularly DroidCon Berlin. If you happen to drop by that, there's a lot of low-level stuff going on there. Slide 2 of 2. When I was researching this, I came across this website, Awesome Android AOSP, which I hadn't come across before. It's basically a very long list of links to almost everything you can imagine. A lot of it is way out of date, but it is worth a look. And then we have various community support around various bits of hardware. So around boards, we have the GlowDroid community, we have the various Raspberry Pi groups, and likewise around custom ROMs and things like the Fairphone, we have groups, each serving those particular communities, but they have the open source ethos to a large extent. It would be great to share more with these guys. So what could we do? I mean, we could do nothing, but that's not really an option in my opinion. There's a bunch of stuff we could do which doesn't actually require a huge amount of effort. So we could set up storage places to store stuff. So right now there's a GitHub page I have. There's the thing that at linaro.org that Amit has set up. We could do some kind of communication channels. So we have the Matrix channel that the Android developers people have. We could do some social media behind this. And then we could do with some online meetings and maybe in-person meetings. Most of this stuff we do already. It's just kind of fragmented. I'd like to kind of focus this and bring it all together a little bit. And all of us in this room, we can all become advocates for the idea of an open source Android AOSP community. And maybe we should lobby Google to take us a bit more seriously. So finally then, and hopefully I've got a few minutes left, discussion. I would like to have a discussion with the people in this room and the people not in this room about what we can do about this. So quick fixes we talked about already. There's a bunch of stuff we could do with almost no effort. Things that need some effort, well, the leadership thing, it needs somebody or preferably a group of somebodies to volunteer to do some stuff. And I guess since I'm standing here, I'm kind of offering my services here. Things that could require substantial effort. So if you to do this properly, we would need to set up a separate organization, a not-for-profit of some kind, get some sponsorship, get some funding, and so on and so on. So there's kind of 3 levels of menu here. So I'm going to open this out to anybody who wants to say anything. What do you think? What can we do? Is this a good idea?
Go. Okay, it's kind of quiet.
So I think it's a very good idea, but I think there's two big blockers that we cannot really solve at the moment. One is the gatekeeper problem, and you cannot really get code into AOSP unless you have two reviewers, as most of us have probably noticed. And it's impossible to get anything past those reviewers that is not in line with Google's ideas. So, for example, if you want to use AOSP in a context that doesn't matter, that doesn't match their vision of where it should be, like, for example, you want to use it in a headless system or whatever, that is not in the plans there, there's no chance whatsoever it will be accepted. And there should really be more open repositories. Ideally, it would return to something more like what was planned in the beginning with the Open Handset Alliance, where there's more different organizations in control of it.
Okay, I mean, that would be nice, but that's not going to happen, and I don't ever expect that to happen. But there's still stuff that's worthwhile doing. We can augment AOSP by creating our own repositories which append to AOSP. So one of the principles, I think, would be never fork AOSP. That's an insane thing to do. But you can work around AOSP. You can add to it in non-invasive ways, and maybe add in some patches.
Chris. So a couple of things. I think you mentioned that already. At the last Plumbers, we started talking about the debboards for Android part. The .lenar.org is incidental. It was easier for us to manage. But the idea was that we could have developers around AOSP that could come together and talk specifically about debboards that support AOSP. So one thing we were able to do with that, and it's like an open invitation if anybody wants to collaborate, we have a Gerrit. So we are able to have an AOSP style development workflow there. So there is Gerrit, there is GitHub. You can push patches. We can follow the same process as AOSP. That's one. The other part is that we envision with proper support from the community, we could have that as a placeholder for common HALs that can be very useful for people doing almost the same thing, or maybe the same kind of socks.
Okay, that's perfect. Yeah, let's do it.
And then there is a hash AOSP developers on IRC. That's already there, and I think it's fairly active.
I mean, it's a little bit active, I would say. It could be more active, let's put it that way.
Yes.
Yeah.
No, I'm totally agreeing with you in that we need more effort on this.
Yeah.
So, yeah.
And I would like to raise this as being an issue that we can tackle, rather than just saying, hey, we can never win against Google. We can surround Google. We can partition Google. Sorry, that came out wrong.
Hi, I was wondering, and I know the regulations vary by country. I'm most familiar with the regulations for nonprofits in the US, but if you were to be part of an organization in the US, there's a difference between 501c6, that is trade associations, which are which work in the interest of their member companies, and there's 501c3s, which work in the interest of the public good. And I'm just wondering if you see one of those models fitting better for this sort of project.
Geez. I guess it kind of falls between the two. I mean, fundamentally, I'm looking at it from the public good aspect. Us being the public, and we have a need to come together in some way. But I can see also a value of this being viewed as a trade association, as a way of expanding it out of just individual developers. And ideally, we'd like OEMs to be involved. We'd like to be the SoC vendors, the board vendors. We'd like the whole ecosystem to be involved at some point. So yeah, maybe it's more towards the trade association part of it, but this is a detail that would need to be sorted out if we were to go to the next step.
For sure, yeah, thanks. Just making sure it's on the list.
Yeah, got you.
Maybe just a quick side note here. I think this kind of like looks as Google versus the rest of the world, but to Google's credit, Google is actually helping a lot with this. Like Android is so successful because Google is building awesome tools and investing in a community of application developers, right? Like we wouldn't be here talking about using in Android and all these other form factors if it wasn't for that. And that community is very successful and will continue to be successful. And I think what's missing is an equivalent community at the platform level. And I would say that maybe in some cases it's not just like Google that didn't help with getting this formed. It's also kind of what you said, those many small islands that don't want to speak to each other. And there are many places where actually nobody differentiates on some aspects. And actually, if we were to work together, I think that would help. So I think it's, yes, we definitely want Google part of this, and that's kind of what we're saying, but we're also saying that we want the rest of you folks to be part of this. And if you were to be part of it, then Google would probably be part of it as well to some degree. So maybe a call to action to us all in the room besides.
Yeah. I mean, I would like to just amplify that. Yeah, at no point do I want to be antagonistic towards Google, even though I may have said a few things by accident just now. I did not mean them. So, I mean, Google are the good guys here. They produce this huge chunk of code which is used by billions and billions of people, so it's a good thing. Whereas other phone manufacturers don't open source their code, and so we can't make clones of those. So I'm not belittling anything that's done here. I'm just saying that there is a little bit that is missing from the whole jigsaw, and that's the bit that I think we could fill in if we wanted to.
It seems one of your primary users, if you made this happen, would be the alternative firmware communities like Lineage. I'm most familiar with Lineage OS, but there's many of them. And my observation of them is they don't really operate much like a traditional open source and free software project the way we would see it. They just have a totally different community aspect, and the way that they release, the way that they communicate. I mean, I can never, I have to go on XDA forums whenever I have to find a question, which are like impossible to use with all the ads and everything. So I'm wondering if you've thought about how you do that community building, because that's going to be a key piece of your user base. These people who don't really, they want to do open source, they want to do an alternative to Google, because they're supporting devices that Google doesn't support anymore a lot of the times. But there's just such a different community that's so removed from, like, I don't know if there's anybody here from those communities, but I suspect not. They don't come to things like Plumber. So I'm curious if you thought that through, of how to build those bridges that we'll definitely need.
Good point. I mean, I don't have any visibility of those communities. But if anybody, I mean, they would be great people to have on board. I have not investigated how that would happen. But yeah, great idea.
Just a quick point on that. I've been at this conference now for probably 10 years on and off. And if you look at the agenda is very much driven by Google, right? And this is an open source community. Everyone can contribute topics. Why aren't there topics from other folks, right? Android is modified in so many ways. So I think we should probably get our community straight first and try to contribute some more. Try to come here with topics that you struggle with, discuss about them, figure out how we could stop them.
Okay, so I'm out of time here. Just one final thing I'd like to say. If you would like to follow through with this, please contact me directly, or preferably put your email into the matrix chat for this dev room, and I aim to put together some kind of proposal that we can share amongst ourselves and see if we can take this to the next stage. Thank you all very much.
So we've got Dimitri.
you hear me? All good? So, hello everyone, my name is Dmitry. I work at Android Cuttlefish and Android bootloader teams. So, and today I'm going to present you some initiative, which is Android generic bootloader, which I'm a part of. So, to better understand the problem, I think it makes sense to share some context, how the Android boot, how it looks like basically on a high level. So basically, as you, I guess, probably cannot see on a slide, but I will share some quick overview on that. So like, first of all, we're reading some block devices. So verifying this data with a leap AVB. So then like parsing some Android specific headers, like from a Android specific partitions, like a boot, init boot, vendor boot, everything. So, and then like put it together and for example, the kernel, RAM disk, boot config, kernel command line. So sometimes we also need to decompress the kernel. So a lot of stuff there. So then we're building it, everything together and put into some, usually SoC specific place into the RAM. So prepare the board in some ART specific way. For example, for ARM64, it can be like disabling MMU, flashing some caches, and finally do a kernel jump. So as you may guess, majority of this stuff is can be reused, and it's common for the whole ecosystem. Some of the other stuff can be kind of edgy, so like majority of it is like common, but we still need to do some SoC specific stuff. And some of the other stuff can be purely SoC specific, for example, communication with a secure world, so etc. So, and actually, by taking all of that, the main problem we currently have is like a fragmentation on a bootloader level. So, and it's like the main problems about it is like Android boot flow is getting changes some regularly. So we introduce new partitions, we introduce new versions of some partition headers. So, and like we need to make sure that everything needs to be re-implemented and adopted by the various amount of firmwares across the ecosystem. So some of the migration happening, for example, from command line to the boot config, which can be like, it usually take a lot of time due to this fragmentation. So another problem we have, so which is not really related to the fragmentation, is the release cycle of the Android boot logic is mainly, right now it's kind of tied to the release cycle of the bootloader. So if you want to update some Android boot flow, you need to update the whole bootloader, which is probably not something you usually want to do. So also another issue is like documentation, it's maybe not enough. So like we're releasing some specs for every Android release about like how to boot it. So, but it definitely may have some gray areas. So the vendors may have their own interpretation on that. So like, and if we have some piece of code as a documentation, it can be positive to the community. So alongside with this like specs, we will have some production ready code that you can look at and understand how the thing's supposed to be implemented there, at least from the Google perspective. So that's why we introduced an Android generic bootloader, which is like UEFI application provided by Google. So the main values of that is like, it's on a high level about solving all the problems I mentioned. So, but specifically for the partners, it can be useful. We're really bad at supporting the GBL, adopting it at the first step, and then supporting it for some future changes we are doing there is like, should be easier than re-implementing the whole stuff and then support it. So, and also like solving the documentation problem. So if you have like a reference implementation, use it on a production ready devices. So like it's a good piece of knowledge. So we can all learn from. For Google, its main value is like to basically move faster in this area. So if you have like hundreds of different firmwares implementing the Android boot flow over and over again, so it's kind of hard to make any changes and expect that it will be adopted by the whole community. So, but if you have some like the piece of code that can be reused and can be valuable. So, and also we can make sure we use some upstream, at least from AOSP perspective, components such as like leap, AVB, etc. GBL from the technical perspective is currently a UEFI application written on Rust, so without standard library. So we support dynamic allocations backed by UEFI allocation services. we already supported all architectures that used across the ecosystem, at least the popular ones. So it's available as a part of the AOSP and developed there. So like it's fully transparent. It's built by Basil. We compile it against the upstream from the AOSP perspective toolings. So, and it's going to be shipped as a separate partition, which is like ESP AB partition on your device. And we're already using the GBL to boot the cuttlefish. So not by default for now at least, so, but we definitely have some future plans on there. So why do we decided to choose the UEFI? So the main reason for that is like it's already adopted by some of the big partners and used on their production devices. So like they have some like, it's a big, good proof of concept here. So like it's also advocated by ARM System Ready initiative. So like it's already kind of used by the ecosystem here. It's also supported on some of the bootloaders already. And like, as I understand, the Google done it for the U-boot. So like, and we definitely have some future plans on there. So the UEFI interfaces mechanism, since I mentioned that like the whole bootloader Android thing is kind of fragmented. So we, like UEFI interface is providing us an easy way to make some custom stuff here and there to make sure, at least on the early stages, that GBL is kind of easy to adopt. So we already have a lot of like drivers for existing hardware we are already relying on. I'm going to cover it on the next slide. So UEFI runtime is kind of stable. So 2.10 specification is like 10 years without any changes, I guess. We also considered a couple of alternatives. So the main one is probably a core boot. So, but according to our understanding, so if we use a core boot, we need to force all our partners to open source their firmware, which is like will be definitely a hard thing to do, especially with big commercial companies. So like ask them like just do the open source for your firmware right now just to support the GBL. So like it seems like not gonna work. We also using the U-boot to boot the cuttlefish, so that's we kind of support the Android boot flow there. So and sometimes we're making some upstream work from like AOSP version of the U-boot to the mainline one. So but it's also kind of not solving the main problem of the fragmentation because we cannot force the whole ecosystem just to use a U-boot or any other particular solution. So we already supported a couple of main UEFI interfaces right now to do the boot, but as I mentioned, we have a lot of vendor SoC specific stuff, so that's why we introduced some our own custom interfaces that like we definitely have to have at least on the early stages to make sure that like we can realistically look at the current fragmentation situation and like support all the possible boards and let SoC do their own specific stuff on some different stages of the Android boot I mentioned before. So like important note to mention is like our UEFI interfaces are not really finalized fully. So, and like the API may change, etc. Because like we are definitely working with the partners with some dev boards to understand the all possible cases better. And and only then we will be able to came up with some final APIs here. So, but I will go through some of them to mention like some rationale behind some of them. The first one is like to run the operation system, we need to pass some configuration to that. In the Linux case, so it's usually device tree, command line, boot config, stuff like that. So currently we're building it from the artifacts that built by Android build system. So, but some of that artifacts can be reused across multiple SoCs. So for example, only bootloader and SoC may know which particular base device tree to choose and like which overlays to apply, which like some other changes that can be SoC specific as well, we need to apply on top of that. So we're definitely providing some ways to customize that. Another one is like a slot thing. So because as I mentioned, GBL is going to be part of the ESP AB. It means that firmware needs to somehow choose like which slot to use without the GBL. So like we're definitely relying on this AB logic that implemented by the SOCs for now. So that's why we have a custom interface that like GBL will rely on as well. So fastboot is interesting topic. So it's not about how the Android boots, but it's still the big part of the Android bootloader. So, and it's the majority of the fastboot is again getting re-implemented by the vendors over and over again, especially the device part of it. So that's why we bring the fastboot with the GBL as well. So we already supported 2 transports, so like a TCP via some low-level UEFI protocol, and also USB via our own custom protocol, which I'm going to cover on the next slide. So the one note about the network, so like we decided to go with a low-level network protocol rather than relying on something more high-level, such as like TCP, UDP protocols, because some of the firmware may have a very limited network support. For example, according to our experience, U-boot right now, so like it's the like TCP stack there is not really fully done, etc. So like that's why we're bringing our own TCP stack embedded into the GBL, so to make sure we support as much platforms as possible. So the USB protocol I mentioned, so like currently some default UEFI USB protocol is kind of hardware aware, and we definitely don't really want to know all that information inside the GBL to make a decision how to initialize your USB stack, etc. So that's why we have like slightly more high-level protocol. We just care about like how to start USB, how to stop it, and how to send data both sides. So that's why we have a high-level protocol. So like, and at least for now, the partners in the community will have to like wrap their own low-level SOC-specific protocols and use our own one to the API to give a chance GBL to rely on it. So the fastboot, as I mentioned, like it like majority of it is common, the whole protocol, the whole stuff around that, but vendors still doing some custom stuff there. So for example, custom fastboot variables, custom fastboot commands, and we definitely want to support that. So that's why we have the GBL specific protocol, so where you can add your commands, variables, etc. Or like, for example, if you wipe your user data, so like here some SOC specific stuff may happen. For example, like to wipe the whole secure world, which is also can be very, very SOC specific, at least right now. So, and what are our future plans here? So it's definitely right now at this stage is like working more with the partners, also like bringing it up to more hardware. We're already doing it on some of the dev boards, but to better understand all the possible cases and to be able to come up with a good APIs on that, we need to learn about the real hardware cases. So that's why reach us out if you want us to help you to support your board and run it with the GBL. So it will also help us to finalize all the UEFI interfaces we have. So also, as I mentioned, like not all firmware currently supports the UEFIs. That's why we are working on that as well. So like we are bringing the UEFI runtime to the little kernel, which is widely used across the ecosystem. We already merged some of the basic UEFI stuff there and working towards it. So, and probably as a result in the very end, so like it would be something, bring more standardization here. So like we will get rid of our custom interfaces to make sure so adopting the GBL is kind of, it's at least easier than re-implementing the whole stuff in the very end. So some useful links here is like source code is there, so like also some documentation about how to use GBL and how to run it with the QEMU, with the cuttlefish. So all the development is happening, all the PRs from our side is happening on the AOSP as well, and also some points of contact if you want to reach out our team or like me in particular. And some topics we are interesting to hear the opinion from community. So like it's basically everything I shared today on a high level. So also another one is like we definitely want to learn more about when you do and in which particular places you're doing some SOC specific stuff, particularly on a like what you're doing with a device tree, what you're doing like with everything. Also like UEFI is kind of single threaded thing by design. So we are currently adopting some async protocols to do some stuff in parallel if the firmware supports that. So like, but we definitely want to learn more if you do any parallelization with the UEFI, so please share it with us. So overall, yeah, thank you. Looking forward to hear your questions.
So moving to EFI makes me sad generally. I'm bummed that ARM ecosystem is moving in that direction. So my question is, what about core boot? What if you have a device that's running core boot and you want to use the standard boot, like the standard boot method, which I think is great to defragment the ecosystem? Would it be possible to add code to GBL to make it into, you know, so you could build it as like a core bootloader or an EFI bootloader? Is that something that you would be open to, or do you really want to push everyone to UEFI?
So we definitely, so we don't have the final solution, final kind of opinion on this right now. So like, we definitely don't want to push everyone to use the UEFI. So, but according to what we hear from the partners right now, so UEFI is kind of more preferable. But if we have some like big guys who want to use the core boot, we will definitely think about like how to have another layer to abstract from the UEFI and support some other stuff. So like, we are keeping it in mind. So, but currently we never heard about like anyone big want to use a core boot for that. So like, but if we do so, okay, reach us out. So like, we definitely want to hear more about it.
Yeah, so you say, you're talking a lot about partners here, and I'm wondering also about consumers. Like, I mean, in you know, the talk that Chris just gave, it was a lot about, you know, who's consuming this stuff, and I think I just wonder, you know, given that Chris is talking about trying to, I think, reduce fragmentation here, I just wonder, and I wanted to clarify your, it sounds like the reasons you don't want to use U-boot and core boot are because of the license, which is the same license that Linux uses in those cases, and instead opting for something that lets people much more easily fragment the ecosystem because they can just proprietarize whatever changes they make. So I'm just wanted to clarify that because it just seemed a bit confusing to me, and just make sure I understand the reasons for not using those other tools.
Mm-hmm. So to get rid of the fragmentation is like, we definitely need to have all that big guys on board. So like to support the GBL. So like, and if we force right now to use something like which requires them to open source their firmware, it's just not going to work according to the initial feedback we get from them. So, but as we discussed before, so like, I don't know, probably in the future supporting something like core boot is like the whole thing is already launched. So like majority of the Android devices are booted using the GBL. So like, and getting some other people core boot specific stuff to support that. So it's definitely something we would be open for. So
okay,
like
yeah,
UEFI is just a thing easy to start from. So that's why we're doing it.
Yeah, okay, I guess I understand. It just seems odd, like Google can tell them what to do. I feel like it's not like you have to cater to what they're doing. Like, you own Android, you can tell them this is how we're doing it.
But we definitely need to take their opinion, right? Because like it's not just about the Google like saying what to do. So we're definitely hearing some like opinions from the other companies that's using Android. So and if we force them to do so, like it will be really hard.
I see.
In my experience, Fastboot is very Google specific. So far, the vendors had to do their own implementation. In that sense, this seems like a good idea to control, like put things that are Fastboot specific together and not have the vendors worry about how to implement, boot header image v7 or whatever.
So I have two questions. One, is there any plan to help prevent vendors from forking GBL and it no longer becoming generic if vendors think they need customizations that's not allowed by the EFI protocols? And second, is there any plan to upstream the implementations of the EFI protocols to upstream U-boot? It sounds like that. I'm assuming that's what you're using for Cuttlefish.
So we already have some done, at least on the AOSP side, so like by upstreaming the UEFI protocols, so like, but they're not on the actual upstream right now, at least. So, and the first one, so like we're running out of time, please reach me out directly, okay? Thank you.
Maybe for whatever topics are left to discuss, we can discuss in the BOF. I think it's at the end of the day.
Yeah. There's just one patch.
So we've got Prakash.
For the
DMA buff.
USB gadget. So if you want, I can share that. I mean, it's brand new. We just got it working last week. So, but we do plan to expand that one.
Hello everyone, my name is Prakash Gupta. I'm from Qualcomm and I'm part of kernel team there, and I'll be talking about generic restricted system heap, generic restricted DMA buff heap support. So this is the agenda for today. So primarily there are two parts I want to talk about. One, why we need secure DMA buff heap, and second, what options we have to support it. In Android vendors specifically, we have a lot of downstream secure DMA buff heaps, or we can call it restricted DMA buff heaps. And there is need to upstream them both in terms of maintenance support as well as so that upstream kernel can have features specifically supported by secure DMA buff heaps. So just a refresher, why we need DMA buff heap. So DMA buff is used for sharing buffers between multiple devices, primarily avoiding copy. So DMA buff heaps provide a mechanism for user land to allocate these buffers on top of it where operations we can perform. Now, secure DMA buff heaps, now we refer in Qualcomm as secure DMA buff heap, but while discussing with community, it came to our notice that people not necessarily see them as secure. They can be called restricted or protected heaps, primarily because secure people refer as something THE manages, Trusted Execution Environment, where in our case, not necessarily these buffers are protected through THE. They can be protected through hypervisor or any other mechanism. So what methods we have for restricting the buffer access? One is XPUs, external protection units. And second is through type 1 hypervisor, through stage 2, the buffer access can be protected. Now, though we are using, okay, so why exactly we need protected or restricted DMA buff heaps? There are a few use cases which require HLOS not having access to the buffers, the protected buffers. Some of the use cases are secure video playback. You can probably have used Netflix where the content need to be protected. And fast RPC CPZ, which is compute protection zone, which is used for video post-processing. Again, the buffer need to be protected from HLOS. Now, these can be achieved in existing upstream methods using custom interfaces between user land and kernel. But there are a few challenges I want to talk about, and that should establish need for having secure, protected DMA buff heap. Now, in Qualcomm case, fast RPC is one example where we are allocating buffers from user land in unrestricted heaps. So currently upstream supports two unrestricted heaps. One is system heap and second is default CMA heap. Both are unrestricted heaps, that is HLOS has access to those buffers. Now fast RPC kernel driver protects these buffers with Qualcomm SCM interface. In other vendors, they can have their own mechanism to protect the buffers. Now, the kernel interface is available to protect the buffer, but it cannot be done from user land directly. I suppose there are some concerns to trust user space to protect the buffers directly. Now, without restricted DMA buff heap, while client can protect, so client driver can have the mechanism through custom driver interface. They cannot have direct say over a protected buffer. Now, this takes away the ability for clients, user land, to control over the use case, what kind of memory type has to be used for a use case, and they are dependent on custom interfaces and deal with driver. So driver has to have this kind of logic based on use cases to allocate buffers, which partly defeats the purpose of having DMA buff heaps, which we wanted to give the control to user space. So these are some of the examples of Qualcomm protected or secure DMA buff heaps. We have secure system heap, where the allocation is through system heap, and buffer protection in all these cases is Qualcomm SCM interface. Second is secure custom CMA heap, and third is secure carve-out heap. In all three cases, I suppose other vendors have their own custom heaps where OPT or other mechanisms are used to secure the buffer. But to my understanding, by and large, allocation methods will be one of these. So now, if we have established need for having secure or protected DMA buff heap, the question arises how we achieve these in upstream. One possibility is we can have vendor-specific DMA buff heaps, what is supported in downstream, and the same can be supported in upstream kernel. Now, we take an example of system heap. So a corresponding restricted system heap would have allocation method through the upstream system heap, and memory protection can be done through Qualcomm SCM in Qualcomm case, and OPT or vendor-specific buffer protection method. I suppose Linaro has posted some patches in that regard. So each vendor in this case would need a separate heap based on their memory protection method. So in Qualcomm case, we can take example Qualcomm Secure Pixel will be named heap. In case of a vendor using OPT, it will be vendor OPT named heap will be there, and that has to be used by user land libraries. So in that regard, during discussion with upstream, one thing came up that it is going to fragment based on number of vendors and different protection methods. So one of the suggestions from our side was that can we have internal ops to maximize code reuse and minimize vendor-specific heaps. So these patches are posted in community, not by us, but we have suggested that. So the format is this way, that each heaps can be distinguished with the allocation method and the way you protect it. So they can have their internal ops, and each vendor based on specific allocation and buffer restriction requirement can implement these ops. This should still not solve the other problem. It should still have, for every unique combination, a different named heap will be exported to user space, but definitely it should reduce the code duplication. The other suggestion we have is to reduce number of named heaps, where different vendors have different buffer protection method, is to have named heap based on the use cases. So for example, some vendors may have OPT-based buffer protection method, and Qualcomm may have Qualcomm SCM interface. But both methods, if eventually are requiring a secure video playback, then based on use case, we can have named heaps, and internal platform can take care of mapping the use case heap to write allocation and buffer protection method. That should reduce the number of named heaps, and probably user space can be vendor agnostic. In this regard, in Qualcomm case, we have been working to support secure video playback in upstream, and we have posted on top of the restricted heap ops secure system heap patches, and we have also added support for secure context bank support. Those you don't know, there are two cases where SMMU support can be done for restricted heaps. One is through Opti or TZ, where Opti manages the SMMU context bank. Second is for clients who are managing these through HLOS. In ARM SMMU driver, we need to have support for secure context bank. So this is, though it is Qualcomm specific, this method can be extended to other vendors. And the third is Iris video driver non-secure support. So that is under review and progress. And the last item would be Iris video secure support. That will be done as we get more feedback from community. Yeah, that is the end of my presentation. Any questions?
Yeah, I'm sorry, we kind of discussed that 2 days ago. So were you able to solve the issue of not crashing the laptop if I pass wrong DMA buffs to the driver?
So that brings, so there is definitely a need for, as I said earlier, the use cases are supported downstream. So the other mechanism we have already, where fast RPC example I gave. So if we see that user land is compromised, even those use cases can cause a crash where incorrect information is passed to kernel regarding whether the buffer is protected or not, and attaching it to a non-secure context bank.
Under no conditions, the user space should be able to crash the kernel. So if user space is compromised and it passes wrong data to the kernel, then your driver, and it causes a crash, then your driver is buggy and you have to fix it. So under no conditions, we should be able to crash your driver.
Okay. So I think there can be verification with respect to whether user space. So in this case, what we are proposing is user space able to allocate from restricted heaps, as compared to currently it is allocating from unrestricted heap and passing metadata information to kernel to protect the heap on its behalf. So both cases, I see the only difference is in one go you are allocating from restricted heaps, and user space has control rather than having custom driver interface to indicate to kernel driver that now you have to protect the buffer. So that is the only difference from existing mechanism what is already upstreamed. Okay.
Yeah, I think we're still missing a couple of things in DMA buff in general to do that. Like, I believe it's MediaTek who has been trying to upstream HDCP and secure video playback in KMS.
Sorry, I can't see.
And the way they are doing it is by basically checking the heap name the DMA buff it's importing has been allocated with, which is kind of hackish. But I think we should need like extra metadata attached to the DMA buff itself so that drivers can discover the attributes of the DMA buff it's importing and make sure, like, yeah, when it's importing the DMA buff, you're not importing something that isn't compatible with your current use case.
The other thing I've been, I guess, hesitant about is I feel like the, restricted memory idea has, I don't know if the semantics between vendors is quite comparable. And so I keep on worrying that by trying to put it through a common driver, we're going to end up with, basically the same driver name that has different behavior on different devices. And so I'm still not sure I see the benefit of trying to consolidate everything under the same driver yet. I know you did mention that, they could have separate names and that way we could avoid some of that, but I still kind of feel like the concept of restricted memory maybe needs to get pushed deeper into the memory management subsystem. So it's a well-known primitive similar to CMA. So that, yes, we can export it via DMA buff, but other internal uses can be done with it as well. And since we haven't gotten to that point, I still feel just a little uncomfortable with it. But I don't know. That's my feedback. I'm not super relevant in this anymore. So
I'll try to answer partially like what I understand. I understand from access policy perspective, a vendor may have different access policies. So they may have certain restrictions, what buffers can be shared between what VMs. So we definitely would need some sort of vendor-specific layer before it can be as generic as CMA sort of allocator. Like checks, because I guess one of the question from user space was that whether can user space do something which can crash the system. Now this same applies for kernel. Can we ask to share a buffer between VMs which can cause some side effect? So there can be some checks, but I think from restricted heap perspective, or let's say secure video playback example we take, irrespective whether we protect the buffer through OPTI or in Qualcomm case, Qualcomm SCM or any other XPU methods, the idea is that now HLOS is not having unrestricted access to the buffer. So the vendor would know what kind of restriction it need to apply, and if we leave it to that, the interface is just asking that restriction need to be applied and pass the required information, what buffers the restriction need to be applied. And then it can operate on the regular ops, what it is going to expose on the DAB. So for example, the restricted heaps can have not the same ops, that you cannot mmap it to user space. So those kind of restriction may be there vendor specific. Depending on if for a vendor a restricted heap means it is shared with the HLOS, or in some cases there is no sharing. It is only the second VM which has access to the memory. So that is vendor specific. Right now it is being done, but it is very custom driver. But if we need to support like protected or Netflix kind of use cases in upstream on these socks, then we need to have support for restricted heaps in upstream.
I'm very supportive of this push to get this stuff upstream, because I really do want to see some consolidation there. So I thank you for the efforts on this. But yeah, still.
Any other question? Okay.
So is secure playback currently supported on Android with Qualcomm chips? I mean, you're saying it's trying to be upstream?
In downstream it does.
Downstream it does. Okay. Thank you.
Was your question about upstream? Oh, okay. Yeah, upstream it is work in progress, so it's not supported currently. Okay. Any other? Okay. Thank you. Thank you for that.
So with that, we're on break for the next 20 minutes, and we'll be back at noon, and hopefully we'll have Big Blue Button back up.
Someone has, yeah.
Well, they apparently wanted to reset it while everybody was at break, and they assumed everybody was at break, but we weren't yet. So. Okay.
You knew that already? That's great.
Well, they had a little chat message about it, but that was it. Yeah.
I know what you were saying, but I still would still have liked to talk to you about the whole, heap capability, discovery, whatever thing that was part of the ECC series. I sent a couple of months back.
Okay. I mean, TJ is a person to involve, because TJ is probably the TJ and Sumit are going to be more of the owners than I'm an old man with opinions, and that's like the worst kind. So, like, you know.
Yeah, so I guess what I was trying to work on is, so it's hard right now to get an idea of the buffer you're going to get from a given capability. So like, for example, we had in the camera the need for DMA-able buffer. So like, DMA buffers are the way to go to allocate them, but that is, we definitely want it to be cache. Like, we won't work if it's not cache. And so getting that kind of insight from the heap is the first element. So I try to add an eye of tool and a bunch of flags to be able to query from user space what the heap is capable of allocating, and then asking exactly when you call the allocator tool to like require something, and then the heap tells you yes, no, which like might not be the solution, but has merit of being explicit.
Yeah, so I mean, I guess one of the things that I think is tough is that when you kind of started DMA,
I know,
here's that aspect from well, there's so many subtle variations in what the meanings were going to be for all these different heaps, and so the idea of enumerating all the types just didn't seem really possible. And so the idea of, okay, well, just name them as one of these separate things, and have the interface to be pretty common. I think as long as it's something that we can kind of have as like memory management that as long as it's like solid, like you can check this kernel memory, this like flag, that might be more doable. Right now we don't have any cache memory, so it's not
yeah, there's been a discussion with Sir on the mailing list because he was saying that names should be enough, and I don't really believe that. Like, well, we're saying
I don't like, if you're looking for a feature type that you want to check generically, then it's the names of investment portfolios.
Yeah, and even
it's not desirable anyway because you have to change users.
thing is that you would have a heap that does the type of allocation you want for that pipeline. You don't now. We don't have users like that.
No, but I mean, well, I would be okay with the like the name data to get like let's get the balls for it, the user space know which opens and then fine. But we're not even doing that. Like we have two heaps and we don't
John tried to do the uncached heap. Which would show the difference between uncached.
Show that. We don't have any non-coherent devices that have open source.
Yeah.
Demonstrate.
And so that's why it was short on the pipeline.
But
so if you have a use case,
yeah, like that would be exciting to have those heaps in. But the whole thing is that like these specific drivers that implement the heaps allow the user space, which has the knowledge of what that pipeline is going to be, to kind of pass it all through. And so the idea of the drivers querying or checking, like, you know, other than like exceptions, they can't.
We spoke about this like when we were trying to do ion or streaming and then XML. The idea of trying to figure out constraints in kernel is not happening because there's user space. Every combination of devices will have
now hopefully you have something like what I like to think of as F-stack, right? So like every system, you don't have like a generic like distribution that you can just put on every system and it just goes, right? Like you have to have F-stack that says, oh well, we have this many different files. They're like partitions.
But in F-stack you have options.
Which yes, and so the thing is, but the F-stack like at least gives us a mapping, right? So we say, okay, for this mapping we're going to use this partition, and so like we need like a similar thing in user space that could be more generic. So you say for this use case, we're going to have
something that Prakash was also referring to, which was not something I mean, there are multiple things there also, but with F-tab I don't think it will work. Where if you have a particular heap that works for a secure video player, but also for something else, you could point to the same heap and have redirections, which is dev heap, SVP and dev heap.
What I'm not very happy with at the moment with heap is that it seems to aggregate both an allocator and the attributes the buffers are allocated with. And so the attributes are policy, the allocator is well, whatever you are allocating memory from. So that's fine. I mean, in my opinion, like having one heap for each allocator makes sense, but not giving user space any control over the policy, basically the attributes and so on, doesn't.
So the thing is, the policy is not really a part of DNA block cycle. It's a part of what memory you use. So CMA is on the thing.
Yeah, but CMA can allocate cacheable and uncacheable buffers. It can do
so
both.
we can have another heap that gives you that specification.
Yeah, but then like the number of heaps just
But the thing is that also the number of capabilities explodes too.
Yeah.
And so you still have to multiplex all this. And so either you're going to do it in a flat namespace or you're going to have some variable number of arguments that you have to pass, which we don't know yet. You know.
I use 64 for flags, so I have flags. Power 64, or would you prefer to have like 64 bit?
I think I'd like to have the explicit one, just because
What do you mean by explicit?
well, having it like the name is because you're not going to have all of them on one system, right? So
Will the name be consistent between different drivers? That is possible using the FS-tab.
Once we get it upstream, like whatever name goes upstream is upstream. And so that I want to have like that be one. Right now, vendors basically it's an escape hatch, right? So when we come up with the idea, so one of the things I was trying to think of is cacheability, which if that is truly generic all up and down the stack, that might be something that's reasonable as a flag to it. Just to kind of simplify the fact that we wouldn't want to have so many like extended variants. But there's a lot of stuff that I'm not confident is super generic that people still want to kind of put in as flags. And I think just having more names, and honestly, even if vendors have their own crazy per device names, and so then they have some mapping to this like, again, the partition layout thing. SDA1 or whatever, like, you know, so that it could be whatever that needs to be, but they know that for this use case, this pipeline, because they also know which devices, this one device that we want to pass it through. That's kind of where that has to be encoded, because it can't. There's no.
Yeah, my concern in that is really getting a generic stack setting matter on PSP. And so how does the matter can figure out which heap does it have to use in a generic way without knowing, without having to care about all the other heap drivers I think are sort of
comparing that with the stuff done especially if you're on two probably
Right.
similar.
Well, I mean, this is the thing.
What is your root address on your installation versus mine? It has to figure out from
well, that's pretty easy nowadays, right?
So
you just have a partition with the right UID, and then system automates it, and that's the one with the right UID.
But there is also but there is some not needs to happen. You don't open, you can't open each dev whatever UID. Then the question is, you have to open slash and move it on dev dash. So I think going to be something similar, where you will expect or look for SVP or live camera or whatever heap name, and then on different systems it will manifest as a different per device, but
one device at a time.
mapping because
So you don't have to worry
trying to figure out a very generic way.
Well, okay, but like that's kind of the assumption where you're dealing with one device at a time. All of these things can happen, right? So not only is it like the camera driver, it's the display driver, it's the ISP,
and you have
you
an Android
every
on
device
an Android
that you have.
I think I'm sure
They don't have
so you can
the
do
same
on
constraints.
it if you find these
So just choosing the camera
or even
doesn't
UDEF kind of tools.
because you don't know where else it's going to go.
So the rule,
And the only person who knows where it's going to go is you.
sufficient number of
So it would be like symlink something that was created as
Like I'm to the point where I don't think there is a generic solution. It's much like
that genericity is also
how do you generically map partitions?
like even the name, like let's I
It's
love that
labels.
battle anyway, so like we will use names.
There's something
But
did you have
at
something
the
else
same
in mind
time,
rather than using names?
yeah, now you're told that gives you the name. What the heap heard it well. But then
Problem is evaluation.
like an abstract,
So we try to
something like
with ION
graphic, semantic,
or
or something
and then we
that creates
start
this.
talking about what is on the screen.
So I guess it turns it around. You would that documents what kind of buffers you're getting from the system. Just documentation.
But then would it be exhaustive? So would you be able to say that this is on some Qualcomm device will mean this versus on other devices?
I was about to start a discussion with something like CMA is physically contiguous cacheable, system is virtually contiguous, and I don't know what it is, probably cacheable.
At least that part should be documented. At least we can see this much to take on
I might have completely missed that up.
Then that's a gap on that.
The trouble I worry is that so if it's not there, I will send you the place. Okay. And then we had a discussion that was the latest part of that series about the kernel mechanism, about so I was the thing I was trying to support is basically a card memory and creating a heap from that.
Absolutely have to run into that. Don't have runs in the same row. No, each driver has set of flops. If you have extra users, I'm actually very happy to take insights on all different kinds of files or heaps happening because that opens up a discussion. Right now, most off camera I can see all the discussions. They don't want heaps. They don't want them.
Alrighty. Uh-oh. Oh no.
It's okay. There's only 4.
I can leave my laptop here. Okay.
Oh, to charge?
Yeah.
Wait. Let me give me just a second. Do you have an adapter? He's working on bringing the slides up. I'm not sure what's... Okay. I just wanted to make sure you guys were in. Are you like remoting into this thing?
Yeah, it's all controlled by whoever's there. So this should be able to.
All right, great. Hey, I'm TJ Mercier. It's going to be a talk about MCG and cgroups used by Android. It's been kind of ongoing efforts to update cgroups for the last maybe year or so. Maybe before I start, like if anyone in the room represents a partner who's using cgroups for something non-standard, something Android doesn't use, I'd be very interested from hearing from you. I know what Google does with MCG and cgroups, but I don't have a lot of visibility into what partners are doing, so yeah, interrupt anytime. Okay, so Android is, I think, one of the last big users of V1 cgroups. Now that systemd has basically switched to V2 and made it difficult to, made it a pain to enable V1. But we've started to see some work to officially deprecate V1 controllers, and there's 2 listed here. Yeah, so the general approach has been to like split the V1 code out from the V2 code and separate the structs and put it in a V1 file, put it behind a V1 kconfig, and so that you can support V1 only or V1 and V2, and then the V2 users don't have to pay for the bloat of V1. And then you can deprecate the V1 stuff feature by feature. So that's what MemCG there is in the process of doing. And CPU set is still just got the V1, V2 code split. But you know, I expect to see patches to deprecate more of these controllers over the next year or so based on the cgroup V1 deprecation talk yesterday. So, so what is Android doing for this? Well, starting with MemCG, we're going to try and progressively phase out support for V1 controllers. And by progressively, I mean leave V1 and V2 enabled for release, and then switch the default over to V2, and then eventually remove support for V1 to shrink the kernel size. That's basically just to allow vendors to deal with any issues encountered from doing the V1 to V2 switch. There's been quite a few that I found with MemCG, required kernel patches, but I think we're in a position now to enable that. So, you know, MemCG and CPU set will be the first two, but there's obviously others that Android uses, and those will be coming later. Slow? Yeah, that's what I was clicking. Okay, there you go. Yeah, so some updates for Android 15. MemCG v2 is open for business. There's 2 ways to turn it on. It's still opt-in for 15. It'll probably be enabled by default for Android 16, but yeah, 2 ways to do it. You can enable it on a per-device basis with this product flag, or you can use a vendor cgroups.json override. That flag will go away when we change the default to v2. Another option that you can use in 15 is to adjust the cgroup hierarchy to allow a split between application cgroups and system cgroups. So this is basically aimed at being able to apply controls at just for system apps and just for user applications. Think like protecting working set of sysui or launcher or system server. And you can avoid basically user applications causing reclaim from system applications, and that causes jank. So got a demo for that improvement. So then in 16, further improvements, we're going to turn on this, we've enabled this feature max activation depth, which allows you to shrink the number of total C groups on the system. So that's kind of a problem because some kernel operations scale with the total number of C groups, and the more of them there are, the more time you can spend in reclaim, the more time you can spend with IRQs disabled, and so that can show up as like audio jank, display jank, and so on. So this allows you to control that number a bit and shrink the total number of MCGs. Let's see. Yeah, like I mentioned, it's likely that the default's going to change from V1 to V2 in 16. We'll turn off that, we'll disable that product flag, and that last bullet point, yeah. So it's always been possible to disable MemCG entirely. There's no hard requirement that Android has on MemCG at runtime. So if you find that this V2 transition is a problem, first of all, please contact me. But second of all, we've got an opt-out to work around this. So it's cgroup disable kernel command line parameter. Okay. There are a couple of outstanding issues. First of all, the kernel doesn't tell you how many cgroup, V2 cgroup controllers are actually active right now correctly. The proc cgroups was added for V1 controllers, but it actually just gives you a completely incorrect number for V2. So if you're using that max activation depth feature, it's not going to look like it's working. So I sent a patch to fix that, but Taejun suggested to add a cgroup fs file to display this information. Kind of problem with that is it's a bit expensive to track that hierarchically. It's the same sort of issue that we have with propagating memory C group accounting and stats up the hierarchy. It's costly to move that all the way up, so I mean, I'm in favor of doing it root only, but I'd be curious if anybody has any reason that they'd like to see C group controller counts like at leaf nodes. I'm not aware of a use case for that, but if you got one, let me know. And then, actually, there's another issue not on here, but basically, if you have a very small number of C groups, so typically, Android in V2 will have like a couple hundred C groups, one for each user application and one for each system service, so O of like 200, 300 C groups. But if you enable that app system split and only enable depth 1, and you end up with just like 2 or 3 C groups, the reclaim code, actually, there's a regression in the number of scanned pages during reclaim, and that it shows up as a real big regression in reclaim metrics. So that's another issue I'm actually looking at right now. Those are the only 2 things I know about currently. Yeah, so that's pretty much it with the migration stuff. Haven't received a whole lot of, I've received input from vendors that say they plan to turn on MemCG and they're looking forward to benefiting from the performance improvements associated with it, but I haven't heard from anybody requesting specific features about controlling memory use. So if you have any ideas in mind, please speak up and let me know. Comments, questions? Anybody know what I'm talking about? Oh, Michael?
So we were talking earlier about kernel uprevs.
Yes.
In the field. So if somebody ships a device using V1, say in Android 15, and then in Android 18, they need to uprev the kernel to whatever it is then, Android, or the 7.15
right.
Or whatever it is. They'll have to migrate as part of that uprev, or is there a way for them to continue to use V1?
They'll have to migrate unless they only upgrade to like a lesser kernel. So if they use the Android 18 kernel, then they would be forced to migrate. However, if they do that, they're also getting all of the performance improvement patches in that V18 kernel that make the V2 upgrade viable.
Have you looked at how difficult that would be, though, to migrate as part of an OTA?
I don't see why that would be different from anything else associated with the OTA.
I know it wasn't the focus, but for the CPU C groups, do you see that as likely to actually, like, is there a viable path?
Maybe. So there's a couple of 2 issues that I know of. I haven't looked at CPU set specifically yet, but there's 2 issues that I know of. Actually, one that I'm worried about and one that I know about. The one that I know about is boot time regression, because instead of so CPU sets is used to control whether an app is running in a foreground, background, and that different sets of collections of CPUs there, right? And so we migrate processes between those CPU sets to control which CPUs they're allowed to use. In V2, there's no such migration. So you have 200, 300, 400 C groups. And instead of migrating them, you apply the CPU set attributes to each one of those C groups. And if you have 200 of them that you want to touch all at the same time, that can take a while. And so apparently during, that causes boot time regression. So I have an idea. So one idea for fixing that is just to delay the activation of the CPU set controller until after boot. So I plan to test that, but there's another maybe gotcha, is V1 supports on a per task, on a per thread basis, assigning CPU set attributes, but V2 does not. Well, it does via threaded controllers, But when you have to enable threaded controllers in a hierarchy, which is shared among all the controllers, and that's going to include non-threaded controllers. So I'm not actually sure if we're going to be able to support with C groups the per thread assignments for CPU set. So
the other one I'm particularly worried about is the CPU controller, which we aren't actively using now,
Right.
but I know eventually.
Right.
Because if we do move to the V2 style, when we migrate something, if a task moves to the background, we have to then proportion all of the background tasks to have that same kind of, if we want to bound all of the background under a certain limit of the CPU time.
Same multi-write problem, I think is what you're getting at, right? Like having to apply the attribute across a whole bunch of C groups all at once?
Well, yeah, because we have to recalculate kind of what that single C group's portion of the background limit would be.
But you could also, you can apply these up the entire hierarchy, right? So you could apply this at the level above each application, right? You could apply it at like the apps level, for example. And then you don't have to touch each individual C group.
It sounds weird you have to, but maybe we should talk more about it later. So.
Okay. I think Michael had a Michael.
I only have a comment to this statistics. So you wrote that there's currently only the V1 file, but I think the hierarchic statistics is now merged for 612. So that will be there, the hierarchical thing. Yeah. And I think the use case is the same like with the root one, that it's for, I would say, for debugging purposes when you want to know actually whether there is something leaking.
Yeah. Well, but that's for our stats, right? It's just for our.
I meant the statistics of the number of C groups, if I understand.
Right. So there's nowhere that's reported in cgroup FS now, right? So the suggestion from Tejum was to add a file to do that.
And
right?
it's for 612.
It's not upstream right now.
Not now, but it is heading there.
Oh, there's a patch already?
Yes.
Oh, okay. Okay, I didn't see it.
What I wanted to say, that it's there was the second version of some follow-up to that. So now the V2 hierarchies can provide the information about the number of existing C groups or controller states.
And is it just a hierarchical atomic right all the way up?
Yes, or like it's at every C group.
So it's going to have the same problem that RStat has every time you create and remove C groups.
Yes, it needs to adjust the statistics when you create C groups. So there's
hopefully, okay. So I think most systems don't create and remove C groups as much as Android does. I mean, it's like kind of every app launch, and sometimes for forks, we create and remove these. So yeah, I guess we'll see if I see it in any traces.
I think that currently it has to update the whole path to the root, and there are atomic increments.
Yeah, that's what I'm worried about. Okay, yeah, thanks. I'll go look for that.
Yeah, you mentioned that right now in Android 15 there is a flag to enable MCG V2, right? Do we know if there are any vendors already using them?
Well, yeah, not really. Like I mentioned at the beginning, I know what Google does, but I have very little visibility into what vendors are doing. I can't tell you with any certainty.
Oh, thank you.
Is there any, so you mentioned the system and app splits for the hierarchies. Yep. Is that going to be generic, something that Android does, or is the hierarchy just controlled by the vendor?
Yeah, Android owns that hierarchy. It's tied into how the system libraries work, and if a vendor modifies that hierarchy, it's going to break the system libraries. So yeah, they they can, I guess, append, but they can't really modify what's already there. So I think part of the long-term plan is to provide APIs that allow vendors to do the sort of things that they want to do without going around this system library to do it. But it's, like I said, I haven't received a lot of input from anybody about what they want to do, so yeah. Okay, that looks like it, so thanks for your attention.
Next up, we've got Juan and Kalesh. I wasn't able to update the slides, I'm sorry. It's hard, but hopefully you can point people to the one.
So, yeah. Oh, Kalesh, no one. Yeah. Oh, yeah. So, hi everybody. So my name is Juan and Kalesh. So we are going to be talking about how to bring up devices with 16K page sizes, right? So as of now, we already have 8 pixel devices working with 16K page sizes, and we have a developer option that you can switch the device to 4K to 16K kernel. Sure. So let me go to. So basically, it's like in this slide, you can see like the Android stack, right? So at the bottom, we have the Linux kernel, and the top, we have the applications. And the question is like, which of these layers need to be changed in order to support 16K page sizes, right? So let's see. So here in this slide, basically the layers in green, they have to be changed, right? And that includes also the dark green. So everything, right? But don't worry, we did a lot of work. So, and I forgot the bootloader. So we need to change also the bootloader. So an interesting question is why all these layers need to be changed, right? Why? I mean, why do we have to do so much heavy lifting, right? And here. We can see, like, for example, the RMBA architecture support 4 exception levels, right? And every exception level, you can configure different page size. So you can have the secure world using 4K page size, the kernel that runs in EOL1 using 16K page size, and then the hypervisor, I mean, you can configure it with 16.4K page sizes, right? The architecture doesn't limit you. And if you are supporting second stage translation, then you can have different page size in that area, right? And here is the question, like, if you have to share buffers between different exception levels, it's like, how do you share information, right? So, okay. And in this slide, basically, we have a SOC, right? So in this SOC, it's like on the top, we see some ARM cores and the different like TTBRs to basically that point to the page tables. But at the bottom, we see several devices, right? Most of the devices, Linux can talk with them without any problem, but the tricky ones are the ones like, for example, the root.trust. I mean, in order to talk with them, you have to issue a SNC call, and then it's like you need to, I mean, and once that you issue the SNC call, you can talk with the root.trust. Another device that you might run into issues is the IOMMU, right? That, yeah, you have to configure several things in the IOMMU in order for the Linux kernel to use it, right? So let's see how we can fix all these issues in the different layers, right? So here's the first thing, like, if you have issues in the bootloader because you want to share like memory between EOL1 and EOL3, it's like, how do you share memory? So basically, the ARM documentation mentioned that, okay, the buffer has to be a multiple of the larger granule size, right? So that's the first like thing that you have to do when you share memory between different exception levels. Then the next thing is like the base address has to be multiple of the larger granule. And the third requirement is like, how do you tell the different exception level, the size of the buffer? So the document mentioned that you need to use 4K counts. So basically, you're going to share 32 meg. You divide 32 megs by 4K, and basically that's going to give you the number of 4K counts that you're going to share. And in this slide, you can see an example. I mean, we don't have enough time, but you can take a look later, so how to calculate it. And then it's like, in this slide, we have, how do we fix issues with the IUMMU, right? So when we were bringing up like the Pixel devices, we were running issues with the IUMMU, and what we found after a lot of pain is like, they were using the page underscore size like macro from the kernel to configure the IUMMU. But it turns out that when we compile the kernel with 16K, it's like the IUMMU didn't support 16K. So basically, it's like the quick fix is just declare a macro where you define the page size that the IUMMU uses, and that solves the problem. The other issue is with the contiguous memory allocator. So that many drivers require to reserve memory at boot time. But if they are using CMA, basically you have to have some, you have to keep in mind that with CMA and 4K page sizes, the memory that you can reserve is multiples of 4 megabytes for 4K page sizes. But for 16K page sizes, you need to reserve multiples of 32 megs. So it's something that you have to keep in mind. We are going to talk about that in the presentation in the memory main track. And also another issue that we found is like, in many drivers, when they allocate memory, literally they pass constants as the order, right? So in this example that I put here is like they want to reserve like 256 kilobytes, and they pass the orders as a order 6. So in a 4K system, yeah, that's 256 kilobytes, but in a 16K system, it's 1 megs. So I mean, we discovered this because we couldn't explain several memory increases, and then we discovered, oh yeah, these drivers are allocating more memory than they need. Yeah, and the next issue that we found is in the block layer. So basically, here is the problem. Like when you issue a request to the hardware devices, it's like you need to build a request object, and then that request object is going to have a pointer to a bio, and that bio is going to have a bio back with pointers to the different pages that contains the data. And these pages contain segments. It can contain, a certain amount of segments, but in the kernel, the maximum segment that has to be supported is equals to the page size. And it turns out that there are some UFS host controllers that they don't follow the spec, and they didn't support segments equals to the page size. So what we have to do is like modify the block layer to allow smaller segments than the page size, and the patches are there. So next college.
Thanks, Juan. Next, I will talk about some issues we have when we are migrating the ecosystem, Android ecosystem, to use larger page sizes. So the way we are introducing the 16 KB page size to the ecosystem is through a developer option in the devices. So in a Pixel 8 device, you can just go to developer options and you toggle a switch and the phone reboots into 16K kernel. And for this reason, we need the file systems to be interoperable between 4K page size and 16K page sizes. But most of the file systems, they just assume the block size is equal. They just support block size equal page size, or they just assume the page size is 4K. XFS and ext4, they Well, that turns out to be the case for most of the file systems that Android supports. So,
will work on any size. In Linux, we do assume the block size is smaller, is less than or equal to page size. We're fixing that. But this whole is equal to, that has been a problem for like 25 years. It's just that these file systems didn't care about that problem. So they're just badly written.
right. Yeah. So as Matthew said, yeah, there are some file systems that do.
Oh, yeah.
No.
Probably. Oh, yeah. Yeah, but probably you don't see this issue because when you build the system, you decide, okay, I'm going to build a file system for 4K or for 16K. But for example, right now in the case that we have, it's like we have in the Pixel A device, you can literally just have one file system, and then you can switch 4K between 16K kernel without changing anything, right? And the file system that supports like different block size is X4. So basically, X4 you can run with 4K and 16K kernels if you format the block size with 4K.
Yeah. Yeah, of the file systems that Android supports,
Yeah.
X4 is the one that works out of the box with block size less than page size. And XFS also does, but we don't use that on Android. Sorry. Oh, yeah. F2FS, there was some work to add a 16K block size support to F2FS. But yeah, in this mode, we are using ST4 to switch between the 4K kernel and the 16K kernel. And EOFS is the file system used for the read-only partitions, and GAO also added support for block size less than page size in the EOFS. So some of the issues we had is with certain device hardwares, certain device-specific hardware. So for example, some devices have an accelerator for ZRAM compression, and we found that at least in the Pixel case, the accelerator doesn't work with page size greater than 4K. So to work around this issue, we are in this mode. We are simply using a different compression algorithm to CPU compression algorithm to make ZRAM work. And some of the devices also have the control registers for the mailboxes are only 4KB aligned. And in this case, how we are fixing that issue is we simply just use the mailboxes, which are 16KB aligned. This is suboptimal since we have less mailboxes in the 16K mode, but at least we have a functional device. And this is just to introduce to app developers a device that they can test on. So in this case, it's okay. Yeah. So if you remember the layers that Swan showed earlier, one of the places is in the user space. We have a lot of issues to fix, and these are mostly caused by Android assuming or hard-coding the ELF segment alignment to 4K in the past, and this was done to save some disk space. LLVM is using the 64K as the default max segment alignment, but due to some optimizations in the past, Android made they hard-coded it to 4K. So here I'll explain why that is an issue. So in the top, I'm just showing the VA space and the page boundaries in 4K, and at the bottom part is showing how an ELF is loaded into the VA space. So for each different segment with different permissions, we need to make sure that it is on a different page so that we don't have overlapping permissions on the same page. But because most of the applications are built with this 4K segment alignment in the ELF, the situation we have on on a 16K device is that we can end up with multiple ELF segments with different permissions on the same page, which doesn't work. So we need, on the AOSP side in the platform, we have already fixed these issues. So in your device board config, you can simply enable these two options, Bionic no page size macro. That just removes an assumption from Bionic, which was page size defined to 4K. And the max page size supported, if you set it to 16K, it will fix all the ELF segments alignments in the platforms. Initially, we did try to move to 64K to future-proof against this, but we ended up with some regressions, which we need to revert back to 16K. So yeah, we did try to go to 64K initially, but there were some which weren't acceptable for 64K. Some regressions in the disk space and the end memory. So we think 16K is a sweet spot for now. Is there a question?
Someone has a question?
Oh, okay.
All looking at the camera going.
Oh, okay.
Probably wants to be 64K pages.
Yeah. So on the vendor side, there is a VTA. There are some VTS tests that checks that the vendor ELF are also have the proper alignment. So for the vendor software, you should set this linker flag max page size 16K in order to be compliant with these VTS tests. And some additional changes we needed to do is for the same reason we needed to make art compatible with 16K pages. So when art, this is the Android runtime, when it generates the old files, which are just ELF files, we need to make sure that it generates the segments to be 16K aligned so that it's compatible with both 4K and 16K. So this work is already done and some other best practices are to use the get page size instead of assuming 4K, or sysconf page size. In Android, also the APKs can have uncompressed shared libraries packaged inside of them, and this was done to save some disk space so that we don't have to extract the native libraries, and also for some security reasons. And the way it works is you need to make sure that when you package the uncompressed shared libraries in your APK, they must be aligned to they must be at some page aligned offsets within the zipped APK. And this is because of the loader maps the library directly from the zipped APK. So the mmap offset must be page aligned. So there is a new option in the zip align tool to allow you to specify the page alignment. It can be 16, 64, and you shouldn't use 4K anymore. I guess this is with those changes and hopefully the tips that Juan provided for the drivers. Hopefully, this will be enough for other vendors to also bring up their devices with 16K, with a 16K kernel. So, if you have any.
The default for binaries generated for distros page size. If you stick to a 16K page size, you may have encounter bugs and issues that we don't see in mainline distributions. So this will create more pain for you if you really do this.
We know the LLVM default max page size is 64K, and we initially tried to move to that, but as I mentioned, for the embedded devices, there were some regressions which we needed to mitigate.
For example, we can see that in big servers it makes sense to align to 64K, but the Android devices are like, they they don't have a lot of memory. Like we have devices with 6 gigabytes of memory, right, or less. So when you align to 64K and then you load the program into memory, that means that if the segments are like less than 64K, like let's say that they are 5K, so then you are going to waste in memory 64K minus 5. So basically, that's the amount of memory that you're going to be wasting. And Android has a lot of shared libraries, system libraries, plus all the apps that are going to be loaded. So the wasting was massive. We have tools that calculate the internal fragmentation with 64K alignment, and it was 23% of memory waste. Oh, I'm talking about when you load the shared libraries, like there is going to be memory waste because you have to. There is going to be one area that is not going to be used, but because the permissions of in the page table, in the page descriptors, they have to be set at page table. Like that's the minimum amount of memory that you can reserve. So I'm talking about like if a segment is 4K size, you have to map it in memory that is 64K. So then you're going to waste a lot of memory in the segments. Yeah.
But you're only talking about virtual memory though, right? You can still have a hole where you don't have a physical page mapped.
But the pages. But the pages are 64K, right?
64K.
Yeah.
Yes,
in a 4K device, that will be true. It will only be virtual VA space wasted, but in a 16K or 16KB device, it's both virtual and physical waste. Yeah. Oh yeah, I get it. Yeah. Yeah, thank you.
Next up is Akhilesh.
Hey folks, I'm Akhilesh from Android Systems and Kernel team. So today I'm going to talk about today I'm going to talk about Ublock zero copy, how you're going to use it in Android. So before we go about the solution, let me briefly discuss about the problem statement we have. So in the Android OTA, that is over-the-air updates, the current storage stack looks something like this. So we have a read-only partition called /system. You can think of as a root file system, which is x4.8ofs. And that is mounted on top of DM Verity, and then DM Verity is stacked on top of another device mapper module called DM User. So DM User is an out-of-tree kernel driver which we maintain in Android. So it's a very simple, fairly simple driver. All it does is any IO requests from root partition gets routed all the way to the user space. You can think of like a fuse, but this happens at the block device level, block layer level. So the IO gets routed to the user space. So we have a daemon in the user space which implements the snapshot logic, wherein it checks how do we handle that specific IO request. So why do we need this snapshots? So that is the next slide here. So Android has a specific OTA format, which is very custom specific. So when we compare two image files, which is block devices, we encode 4 different block level operations. So let me just focus on 2 operations here, which is the pain point which we are actually facing right now. One is the copy operation. So what it does is that if you see here so between the source image and target image, we have like 3 copy operations, meaning that on the target image, block 0 is actually just shifted from the source image with block 1. It's just shuffling of blocks between the source and the destination. We call it as a copy operation. And then the second operation is called the replace, meaning that the entire block, when I say block here, it is a 4K block. So when we say a replace operation, the entire block is rewritten, which means that we'll have to write that entire block. So we encode that data in a compressed format and stash all this in a block device. So during OTA generation, we encode all these operations and store this in a block device specifically. So all the copy operation will just take metadata format saying that what blocks have been moved. But the replace ops are the heavy operations because it encodes the data in a compressed format in the block device. So all these operations today, that's how we implement this in the user space through the snapshot mechanism. So if you look at the I/O path for the actual copy operation for a single 4K block size, you see here 3 towers here, right, from a flame graph. So what is happening here is that when we get an I/O request for a copy, meaning that, hey, get me the data from block 0, the I/O goes to the user space daemon, which is nothing but the leftmost tower here. The daemon gets the request from the underlying block device, and then gets the data to the user space, and then sends the data back to the kernel once again. So there is constant back and forth data movement between user space and the kernel, even though the data is not manipulated anything in the user space at all per se. That's for the copy. But for the replace operation, it is exactly a similar flame graph, but once we get the data to the user space, we decompress the data in the user space and send the decompressed data back to the kernel. So the primary problem here is that we are spending a lot of CPU cycles unnecessarily. The data movement is happening between user space and the kernel. So for instance, as you see here, about 15% of the CPU cycles is spent just moving the data from the kernel to the user space. So this is another view of the same 4K I/O request from the flame graph perspective, wherein when the application, our most beloved FIO application, when we are sending an I/O request, 4K I/O request, it's taking about 100 microseconds to actually finish, even though the actual, at the bottommost UFS layer, it's about 25 microseconds. So if we scale this, for instance, what's the problem with this is that, let's say we have an 8 gigabyte partition, and if we split that 8 gigabytes with a 4K block size, we have about 2.1 million blocks, 4K blocks. So 2.1 million of 4K blocks taking 100 microseconds means about 210 seconds, which is about 3.5 minutes. Meaning that once we reboot the device after an over-the-air update, it takes about 3.5 minutes to scan the entire partition. Although we do parallelize things and get down that number today, but that is at a trade-off wherein we are taking more CPU cores. So that's the fundamental problem here with the copy as well as the replace operation. So how do we address this? So there is ongoing update upstream work going on right now with Ublock zero copy, primarily driven by Ming Li. So we did a prototype of incorporating Ublock into the existing storage stack, wherein we mount the slash system on top of Ublock. So that removes our tech debt of removing DM user. And then the current upstream work of using zero copy, meaning so Ublock, as some of you are familiar with, is based on IO-Uring framework. So what it does with zero copy is that you have just one syscall, IO-Uring SQ enter. You send the data to, so the leftmost tower here is exactly similar. You're actually getting the data from the underlying block device, but the data doesn't go back to the user space. There are two SQE buffers which is being shared within the same SQE group. So the data is just migrated within the kernel itself. So the whole idea here is that we move the complex metadata operation to the user space, but the data migration continues to reside in the kernel itself. So we did this. We took the Ublock zero copy patch upstream, the V5 patch upstream, and ran this on Pixel 6 running Android mainline. So we were able to get the same perfecto traces. Now, as you see here, there isn't much back and forth kernel and user space movement. And the latency cuts down literally by about 50% right now. So that's a big win. But there are some still open-ended challenges here. Although the Ublock zero copy is very promising, it addresses 50% of the problem. But the other problem is the replace operation, as I mentioned above. We store the data in the block device in a compressed format. So with zero copy, what happens is that what we really need is once we get the data from the underlying block device, we need to decompress the data. Today, that decompression is happening in user space. Instead of that, what we really need is we need to decompress the data in the kernel itself and send the data back to the user space application. So with that, that will be a big win. So that's the another extension of zero copy which we are looking at. Yeah, that's so I had a chat with Ming Li, who's working on the zero copy, and he was gracious enough to give us a couple of suggestions on how to extend this. There are a couple of ways to do this. One is through BPF. Ublock currently supports is being explored through use BPF, wherein you can explore kfunc to do the decompression in the kernel itself. And the other way is to add new IO-URING opcode, wherein the new opcode can be used to tell what kind of decompression logic to be used for. So those are the two exploratory paths we are exploring right now, but if there are any other use case or suggestions, we'd be happy to take a look at. Questions? So the primary motivation here is to cut down the post-OTA boot time. That's the primary motivation, and also reduce the CPU contention, because we have seen primary concerns with some of the low memory device, wherein like watch and Android TVs, where they constantly run into ANRs post-OTA boot, and addressing some of these concerns is the primary motivation here to drive this further. Sorry? Yeah, so if you have any other use case, for instance, I had a chat with the upstream maintainer of Ublock, and the other use case is being looked into is the QCOW2 compression. So Ublock currently is being explored to use compressed QCOW2 image. So that's the other use case which we are looking at as well. That might primarily fit into the same problem what we are facing right now. So we'll be looking at exploratory paths and sending out some of those patches in the next upcoming quarters. So, but if you have any questions or suggestions, please feel free to reach out.
So the next one's going to be, I believe, partial remote, Chinua Berry. I don't know who's going to be presenting.
Hello? Can everyone hear me?
Let me make sure you're the presenter here.
Hello?
All right, you should be the presenter now, and you should have control over the slides.
Yeah, yes, okay. Okay. 我点。Sorry, I can't control the slides. Wait, 不行。Oh, okay, I got it. Hello, everyone. I'm Hailong from Oppo. I'm happy to share a topic, product practice or large folio on millions of Oppo Android phones. Before the mainline introduced the MTGP, Oppo has already implemented 64 large folio. We primarily use large folio during page faults. In the page fault handler, large folios are used at first. If that fails, use small folio instead. The battery allocator becomes fragmented after the system has been running for a while and may not able to allocate a large folio. To address this, we implement a large folio pool. This pool reserves original memory after system boot and splits into multiple large folios and then adds them to a list. An interface is provided to allocate large folio from this pool. The allocated large folios in a page fault handler would be added to LRU list. However, if we use one LRU list, when trying to allocate a type of folio, the tail of the list could be packed with other type of folio, which would block the allocation. To prevent this, we place large folio in a separate list, the do list. We also use dual VRAM, one for small folio and the other for large folio. There are two reasons for this. One small folio can cause swap slots fragmentation, while large folio require contiguous swap slots. The second reason is that we configure different compression algorithms for different VRAMs, as shown in the figure. Using this standard on large folios provides better compression ratio and faster compression and deep compression speeds than small folios. In certain cases, we allow drivers to use large folio. For example, when many apps are running in the background and launch a camera app which requires a large amount of memory. In this case, background apps may be killed by low memory killer, and the large folio could be released back into the large folio pool. However, in this case, camera needs lots of DM buffer. Therefore, to make better use of a large folio pool, we allow the driver of the system heap to use large folios. As expected, using large folios significantly reduces TLB misses and page faults, resulting in performance improvements across many cases. In benchmark type case, run bench improved by 30%, Android bench by 16%, and AnTuDo scores increased by 22,000 points. In user case, app launch time improved by 10%, and frame drops were reduced by 35%. We introduced large folio in OKI and added thousands of lines of code to the source, which made it harder for us to maintain. As a result, we worked with experts from Google and Linux community. For now, some of the code has been refactored and merged by upstream. For example, Ryan introduced MTHP to replace large folio, while David, Barry, and Chuanhua support MTHP in other parts of page fault handler. Other parts have been merged into Android common kernel. Here, I would like to special thank to Yu, who introduced the TAO virtual zone and implemented the MGLRU per zone list to replace large folio pool and dual LRU. Additionally, thanks to Chris, who implemented the swap allocator to solve swap fragmentation. And here, we would also thank to Suren and Clash, who worked hard to backport all of this work into the GKI. There were more than 200 patches involved. Okay, the final part is QA and discussion. This part Barry will lead it. Thanks. Hi, Barry.
You mentioned the system heap was one of the potential areas where there's a benefit. Was that patch submitted upstream?
Hey, hello. I think I'll take a presenter. Yeah, it's like Hailong has introduced what we have done in OKI Kernel and what we have done in Linux community. Work together with Ryan and work together with Chris and Yu Zhao from Google, and we try to merge as many patches into GKI to reduce the maintenance efforts from us. And right now we are still profiling the MTHP performance in GKI kernel, and some patches are still ongoing in GKI Gary system for testing. And except those jobs in Linux kernel, when we support OKI, when we supported large folio on our OKI kernel, we have actually modified a lot in user space. For example, we have modified the gmalloc. Gmalloc is the native libc, which helps allocate native heap. And actually in gmalloc, a lot of like the Madvise download or Madvise free are not aligned with large folio size. So the original gmalloc will cause a lot of splitting of large folio, while Linux kernel should indeed coexist with the aligned memory management source code from user space. That if user space can be aware of MTHP size, it should be much better. Because, for example, if gmalloc and Java heap like Arch can manage folios, can be aware the MTHP size and then do Madvise download or Madvise free based on MTHP size. That means we are not going to split MTHP in kernel, but right now, actually, we are seeing tons of splitting in Linux kernel. Just use the default gmalloc or Java heap. So luckily we could work together with the user space guys to optimize Scudo or gmalloc or art to make user space source code aware the existence of MTSP. Right now, actually they don't. And the other thing we might want to work is actually right now we only support anonymous large folio. So that means in the system small folios and large folios coexist with each other. Sometimes it can cause another problem. Is we have two kinds of small folios. We have two kinds of folios, and their sizes are different. So sometimes it makes like memory reclamation quite complex. So if we can, for example, support large folio in F2FS and EROFS, then almost most folios in the system will be large. Then things maybe they're not so complex. For example, maybe right now we have to use like virtual zone and the per zone ARU list, and we still doing a lot of like adjustment to make per zone MGLRU work well. In the case we have large folio and small folios coexisting in the same system, and we are still seeing some memory reclaiming issues. Sometimes, for example, we can say like file folios are seriously dramatically reclaimed, and we can say a lot of file reports using the current source code. So we are still trying to fix this issue. So basically I'm seeing.
Ryan, I was just going to make the comment you were talking about file back large folios. I mean, I've said it in the past that I think once we get file system support for large folios in Android, it will improve. It will decrease the fragmentation we see, and it will improve our chances of allocating large folios. I think, though, having discussed it with more people, I've heard figures quoted that somewhere between 80 and 90% of memory used in Android tends to be anonymous, which suggests that potentially it may not help as much as we think it does. So it's just a statement there. And then further, but I do think that it will help us a lot with ITLB pressure. So if we can start mapping much more code using 64K folios and even 2 meg folios where it makes sense, if we can do it intelligently, there are actually big benefits to performance through reduction of ITLB pressure.
Actually, the major problem is actually F2FS doesn't support large folio. Actually, Gaoshan has already enabled large folio support in EROFS, but we haven't tested it yet. So since F2S doesn't support large folio in the ERFS, it's not the mail file system, it's just the system partition, and most file back folios are actually from F2FS. So I don't think ERFS can change things a lot.
Sorry, this is Matthew Oggs. Yeah, I think you should try some experiments with other file systems that do support large folios. But if what Ryan is saying is true, and 80 to 90% of the memory in an Android phone is anonymous, then having small folios in the page cache isn't going to make much difference. Like the problem here is going to be, why are we allocating small folios for anonymous memory at all is the question.
So basically, with like a without virtual zone, actually we have improved like the success rate of large folio allocation a lot, but we still seeing a lot of case we fail to allocate large folio. So in this case, we have to fall back to small folio, and yeah, like the problem is here. We can't like using without pad set. We can configure a virtual zone for large folio, but we can't set it too large because in many cases, like we need file back the folios. If we like configure it the virtual zone too large, then the file back the folio might neck memory. So yeah, so that's a problem. So we can in our right now we set the percent, we set 30% of memory as virtual zone, and we still saying like around 40% of failure of large folio allocation. But we can't increase the virtual zone because otherwise we will neck folio memory for fallback.
I wonder if the problem is that we're using the wrong GFP flags, because for large folio allocation, I initially just copied what we were using for transhuge light, which is, if we have it right now, then return it. If we're falling back too readily, then we're going to see a lot more small folios in the system, so it is going to increase fragmentation. I wonder if we need to use, if we need to actually try to do a little bit of reclaim, even when we're allocating, order 2.
So just to follow up on that, I think for anonymous MTHP, the SysFS exposes knobs to control how aggressively you want to allocate. I imagine they're by default, I think they're by default set to only get them if they're available. So maybe that's an experiment we could try to see whether that helps the situation. Have you looked at any of that stuff, Barry?
Actually, for the first question, I didn't get the second question. For the first question, like if we have tried to like set direct reclaim for large folio allocation, actually we didn't. For the second question, I didn't get it. So can you repeat? Sorry. I've answered the question maybe from Willie or someone. I can't see your face. Like if we have tried to like enable direct reclaim or some memory reclamation for large folio allocation. Actually, we just use the default configuration like the light, transparent light. Yeah, that's what we are using right now. But I agree. Maybe we can try to enable direct reclaim for large folio allocation.
You should reach out to the Bionic team. You should definitely try using Scudo and maybe redoing some of these modifications around Scudo. I think otherwise there's a lot of testing that you're probably missing out on, especially for art system play updates and other updates that come over project mainline. But yeah, you should reach out to the Android memory, to the Android native team. I think they have a public mailing list.
Yeah, for Scudo, actually we compare the JMalloc with Scudo, and basically we find the JMalloc perform better than Scudo, and basically Scudo is using more memory than JMalloc, so we haven't dug into the detailed reason, but right now, since we are seeing JMalloc performed better than Scudo, so we are still using JMalloc.
Real time. Okay. Any other questions, either for you, Barry, or the Oppo team, or anyone here? Okay, thank you.
Thank you. Thank you.
Thanks so much, everybody. That is the micro conference. Once again, thanks to the sponsors, and thanks to all of you for coming out and participating. It definitely is great to see everybody's faces and get to have a good discussion. We will be, I'm sure, writing up summaries and trying to get some of the details published. If folks have anything they want to include, any of the notes, please reach out and let us know. So, all right. Well, thanks so much. Have a good lunch.
Thank you.
Oh yeah. So there's also an Android BOF. I'm sorry. This afternoon or this evening, I guess. It's, I believe, the last BOF slot in the day. So definitely come and bring some topics, and we'll try to get through what we can. So thank you so much.
Thank you.
Shall we do an MC photo?
Yeah, that's true. Let's do an MC photo.
Yeah, no, unfortunately, Sunny had to bring it, and I meant to take a picture of us on my laptop.
Hey, we've seen you for multiple times. Thank you for your review. Okay, yeah, I'm happy that you were so responsive. So I'll try to do better for next time. It's the first time I tried this, so I didn't really know what the procedure is. Yeah. Of course, it doesn't make sense to have a lot of samples for one specific SSD when it does something that's supposed to be generic. Right. The feedback. Well, and you know, the SoCs that came on board 4 years ago when we started this, we had all the same. Thank you. Break these up. Let's get just the ones we need. So it's. I'm actually excited that it's possible to add more architectures in the public build base. I didn't know it was possible. And we'll check this instrument will follow. That's what I'm working on. I don't know if you heard that they really want. Should I
Actually, Blastomir's going to be the one to do. He's going to upload the slides. I see the mic is still live, so that's cool.
Nobody has more than 200 slides. I had one at the referee trial actually. They wanted to do 253 slides.
Wow.
And BBB doesn't support it.
Right. Good. I'm glad BBB doesn't support that. That's a good thing. Because everyone's got 15 minutes, so that's 900 seconds. Okay, still 200 slides. It's not that kind of conference. Yeah, I'll make sure no one sees that. That's fine.
didn't connect, but so who's the presenter now? You?
Yeah. There's some I really don't know. So the cursor should work, right?
Okay. Do it again. Let me check if it changes there. Because during the Android, okay, there's a bit.
It might be a bit delay.
Okay.
And to select your slides, there's this plus, and yeah, the order of the sessions.
Okay.
So what is this ready button? I see no ready button. This slide says, let us know you are back by clicking the ready button.
Ask Steve. Lower right corner. I don't know what he meant, really. But, well, the point of this is to let the remote people know that we are still on a break.
Oh, it is disconnected here. Oh.
Well, Vassimo did.
Yeah.
Let's hope the remote presenters have no issues.
Yeah, right. What do we select which one to go to next?
Plus button.
Plus button. Okay. And then we just choose. Okay, great. Thanks.
Is it sturdy enough? Laptop's falling inside. Was it Dublin?
That was Dublin, yeah, yeah. That was fun.
So should we do it in Japan next year?
That's a good question, actually.
I mean, in December it's very far from.
Certain.
Huh?
It's still not certain.
Okay.
Things may change.
But if it's Japan and it's early December, it's quite far from LSF time-wise. April.
Montreal. Oh, okay.
Montreal's a really nice city. I mean, I wouldn't say it's as nice as Vienna, but it's the most European city in North America.
Yes. I heard good things about it. Huh? Montreal is the most European city in North America, 100% agree.
So, yes.
They can, will they?
In Montreal, absolutely. Anywhere else in Quebec?
What was the question?
Do they speak English?
Ah.
They speak. I never had problems.
Not in Montreal.
No,
Other parts of Quebec.
I traveled throughout there because I live in New Hampshire. And,
Oh, okay.
Yeah, so we traveled by car.
Mhm.
I've been like in other parts of Quebec.
The places I've been in Quebec where people just have zero words of English.
Wow.
Yeah.
They just didn't know or they didn't want.
Well, I would say don't want to.
I think they don't want to. Yes, that's. I think that's the right answer.
Yeah. The next person.
I think they hear that I have accent when I speak English, so they keep hearing and they don't try to like force expansion. Like they think, okay, like he speaks another language as well. Yeah.
It won't be difficult to us.
Catch good work.
I'm not the first speaker.
No, you're second.
Yeah.
Soren's first, you're second.
Budu před přeskokanama, víš. Jako. Budou přednášet všichni 4? Jo, dobrý. Jsem si říkal, že do té 4 hodiny to jako...
Okay, we're starting in just a minute. Hi everyone, welcome to the last session of Linux Plumbers Conference 2024. Thank you all for coming to the track. If you weren't intending to come to the track, probably a good time to leave. Vlastimil and I hope you have a good time. We have a lot of tracks to get through, a lot of talks to get through on this track, so everyone gets 15 minutes, and Soren's going to only get 14 because we're doing the introduction. But we do need to start by thanking our sponsors, without whom we would not be able to put this conference on. And I need to remind everyone of the anti-harassment policy. It's fine to say something's a bad idea. It is not fine to say someone's a bad person. Okay. Anything else we need to say? No. Okay. Fine. Then Soren, you're up.
Hello, everyone. Can you hear me? All right, great, thank you. My name is Suren. I'll be co-presenting with Saurav from Google Infrastructure Kernel team, and we'll talk about allocation memory profiling, the current status, some results from the deployment, and also some of the next steps that we are planning to do. Let's see. So just a quick overview, memory allocation profiling. In essence, basically, it's an option that we can enable in kernel config option. When enabled, it exposes proc alloc.info procfs file, which contains locations where allocations are made in kernel, total size of allocation made at that location, and total number of allocations. So basically, it provides information about all the kernel allocations along with some additional information. So the feature is developed so that it has very low overhead and with intentions that it's deployed in production. And the current status is that it's merged in 6.10 kernel. And we are planning to deploy it in Android kernel starting next release, which will be cut from 6.12 most likely. And we are also having deployed it in Google Infrastructure Kernel as a pilot program, and which involves over 1,000 servers. So we will next we'll present some results from that deployment, and Sarah will present that.
Thank you, Suren. All right, so I'll talk about the deployment of memory allocation profiling. With the goal of reducing wasteful memory overheads, we ran a pilot program consisting of standalone testbed machines and even 1,250 production machines. From there, we gathered the alloc info and we stored it in a centralized DB in an automated manner. And then we built dashboards for visualization and tracking, as you see on the right-hand side plot. Each and every line corresponds to a different allocation call site, and we have grouped these allocations based on the subsystem, such as memory management, networking, and so on. Now, while this dashboard corresponds to a single machine, we also have the capability to get the data from all the machines, providing visibility across 0.4 petabytes of data at any given time. From this, we have identified the heaviest allocation call sites, and even those allocation call sites which vary a lot across time. The plot on the right-hand side is a good example of that. So this is the RX buffer allocations made by a specific network driver, and we have plotted the worst two machines. If you look at the purple machine, first of all, you'll see a zigzag-like pattern, and at times the allocation size is excess of 120 GBs. So once we see something like this, the question arises, can it be reduced, or could it be charged correctly? And if not, does it correlate to any SLO violations, such as packet latency or packet drops? Now I want to go over one success story where memory allocation profiling was the enabler, and this comes from the cloud machines. So from a standalone testbed machine, we gathered the alloc info, and we stack ranked the allocations. The plot on the right-hand side shows the allocation size on the y-axis and the stack rank on the x-axis. Each and every dot corresponds to a different allocation call site. And once we had this, we sent this report to the domain experts. They curated reduction plans. And through simple configuration changes, we could eliminate the allocations represented by the orange crosses. Now, this has led to about 7 GBs of saving per machine, which for that specific VM family. And we're aiming for further 2 GB savings per machine. Now, all of this means that there are fewer kernel overheads, leading to more memory available for guest VMs. Now, throughout this process, I want to specify the needs identified. Now, because of using page extension, the memory overhead of using this feature is about 2 GB per machine, or roughly 0.3% of the machine capacity. And also, we observed that the pilot machine spent 41% more time in alloc pages node mask because of looking up the page extension. And another pain point that we felt was the lack of context. For example, on some machine, we saw that XAS alloc resulted in 1.5 GBs of allocations, but we couldn't tell where it's coming from. Is it coming from shemem add to page cache or some other function? So a generalized mechanism to get the entire call stack or the context would be useful. And so Suren will speak about how we plan to tackle these problems.
All right, that gets us into the future planning. So basically what we are working on and what we are planning to work on next. The first thing is to address those needs that were identified, which is basically the overhead. I recently posted a patch set to store the page allocation tag references in the page flags if there are enough bits in the page flags which are available. So the feedback was that configuration is nightmare. We need a simpler way to configure it. So I modified the patch set to have just one config option, yes or no option, basically, to say if it's enabled, then we will try to store the references in the page flags. And if we are successful, we use that. If not, we will fall back to the page extensions. So that's going to be done basically automatically by system, and the user will get a warning that, hey, we are not able to do what you asked for, but so we are falling back, and you have an option to disable this config. Other than that, we are working on a couple of new features. One is using the GFP flags to identify accounted versus unaccounted allocations. Another one is collecting information about average lifespan of an allocation. So for every tag, we'll have the average, how long does this allocation actually exist in the system. That information can be later used to categorize different allocations and maybe group them. There are some, there might be some optimization techniques that we can use. So I'm also planning to bring back the context capture, which was mentioned just now. It's a feature that was included in the original RFC, but then we removed it to simplify the patch set, the first version of patch set. So I'm working on bringing that back and introducing it. And finally, we are also working on some user space tooling to simplify the data collection and analysis. And once we are satisfied with the state of those tools, we will start upstreaming those as well. So I think that's, yeah. So that's the last slide in the presentation, and I'll open it for questions, comments, feedback.
A bit unrelated question to Surav. Are the dashboard processing and everything is open source?
No, that's only internal.
Can you remind me what is the context capturing? What exactly?
So context capturing, basically, it's a kind of a second stage. So let's say you captured the data, you have your alloc info that at this location, this much memory is allocated. You see that it's growing. You don't know who is using it. So you can specify, okay, for this particular allocation, I want to capture context. So context will be the call stacks, timestamps, some additional information that will help you to track down who is actually abusing your system, who is allocating basically, and maybe not freeing.
Okay, so
right.
Yes, that means you will be able to capture the call stack, and you will not need to wrap any common helpers into the macros to make them distinguish their callers anymore. Because that was the main thing we were afraid of. Like for every call site that you cannot distinguish, you have to wrap it. And that's a maintenance overhead. So with this context capture, this won't be necessary.
So no, the context capture is optional because it has additional overhead, right? We cannot capture context for every single allocation. That's why it's built as a two-stage thing. First, you get very cheap way, with a very low overhead, you are getting high-level information about allocations. Once you identify, okay, this allocations looks finicky, I want to look in deeper, you enable context capture specifically for that allocation. So everything else doesn't change. Everything else is still, fast. But for that allocation, when it happens, we basically spend a bit more time to capture the context, get the timestamps, store all that data, and so on. So in a sense, it's built so that it's performant, but when you need more data, you can enable the capturing specifically for the location you are interested in. Enabling it everywhere would not be deployable.
It occurs to me that context capture sounds identical to what you can get with the BPF trace with the K-stack, and so I wonder if you might want to go with making your context capture just enabling or at least creating a trace point for all of those locations, and then it's just a no-op sled until you need it. Then you use an existing, extremely full-featured system to explore the context instead of building your own small duplicate of that corner of BPF trace.
Maybe that would require a trace point for every allocation.
Well, actually,
I guess.
trace point is a bit overkill. I mean, all you really need is a K-probe, which might already be there. In other words, if it's a function and it's not static, it probably has.
K-probe will be there at the lowest level, no prof allocation, right? But then up the call chain, you want the hook for K-probe will be in the alloc pages, no prof. And you'll need the filter, somehow filter the context that get into the point of K-probe itself. The entry for K-probe will be down the call stack, and at the allocation you want to context, maybe it's too late. Like.
I mean, that's okay to the extent that the rest of the call stack has non-static functions. You can see the call. You can see the call stack already, and this is what I'm talking about with BPF trace already having done the work for you, so you don't have to go through and write this. I speak with some experience of exploring running systems with BPF trace and finding out when can I get the calling stack, when can I not, when can I get the return arguments, and I constantly run into this frustration of, well, if it's a static function, it's not there. If it's already a trace point, you've got it. If it's a non-static function, you usually can see it. But all that stuff is there, and that's why I'm eager to see if we can just use it.
Would you consider installing all the BPF programs and everything that you need in the production?
Well, you don't have to install BPF in order to get BPF trace. It's really just a more sophisticated version of ftrace in some ways.
Right, but will you have everything that you need to enable that capturing in the production machine?
I mean, generally, yeah. In my experience, when somebody gives me this thing and says, "Here, fix it," it's running and it's going to reproduce something ugly. Yeah.
Okay, so it's not usually used only in the debugging environment.
Yeah.
It should be available. Okay, that might be an option. So let's talk about it. Well, thank you very much.
Hello, everybody. My name is Peter Tesarik. I would not even call myself a kernel hacker and definitely not a memory management hacker. But there's something that I noticed while I was working on the software IoT code, and I'm very glad I can present it to you and ask for some feedback, if it's a good idea, bad idea, if there's an easier solution, or whatever. Good, let's get started. The thing is, it seems the page allocator does not really provide good service to device drivers. How do I move on? He's this one. Good. It seems that the zoned body allocator was built around this simple idea that we can somehow split the available RAM into several zones, and then the CPU can access all the zones, and then some devices are more limited, so they can only do 32-bit addresses. They will only access the DMA32 and DMA. And if you're really unlucky, you also have a legacy until 8237. I don't think it even is manufactured any longer. And then you're only limited to the DMA zone. And everybody is happy. Well, unfortunately, that's not what happens in the real world. What we really have is different address spaces. We have this physical address space, which is what you get in the CPU, like translated from virtual addresses by page tables. And then you have something that could be called a bus address space. And there can be an offset applied by a host bridge. There can also be an IOMMU, but I'm not showing that here. And the device has its own limitations. It can be even worse. We can have multiple buses on that system, and each has a different offset. So there is no one-to-one correspondence between the physical addresses and the bus addresses. Now, you may ask, okay, but the kernel somehow works today. So yeah, I can tell you how that actually works. So this is a real code taken from the kernel, and there's this DMA covariant OK, and that's a function which just takes a device, a physical address, and a size, and checks whether that address can be used by that device. And if you look at it, it just first does the translation from a physical address to a bus address, which may fail. So first it verifies that the address is even, the given physical address is even possible in the bus address space, and then it checks whether it is within the device's limits. Okay, which is good, but how do we actually allocate? So the thing is, okay, I hope that is still readable. The comments in bold are from me. So the thing is, if you need a buffer, that is DMA-able by a device, then you just first try to get it from a restricted pool. If that fails, try to allocate from CMA. If that also fails, then just like, okay, fall back to the body allocator. And that's somehow sad, because you just try to use some GFP flags. You get the best GFP flags based on the limitations of the device, and then you just call this DMA coherent OK. And if it fails, you just try a different GFP flag and hope for the best, or fail. So, okay. Next thing is, I have only talked about the address limitations. There might be other constraints, like some devices can't work with encrypted memory. SEV always needs an unencrypted memory region. SME needs it if the device is on the wrong side of the secure processor. And this decrypting is a blocking operation, and it's an expensive operation, so we have something called a coherent pool, which just tries to keep around the sum pages, just in case you need an unencrypted page in a context that cannot block. Okay. What can we do better? Like, this has been in the kernel for, like, I don't know, at least decades, like, yeah, 20 years. Well, not everything. The encryption is younger, but can we do better? And I was thinking maybe I could call my talk, can we kill DMA and DMA32 zones finally? But I found that's a bit bold. There are some good things about the memory zones, and I have tried to list some. The best thing about it is it provides some dedicated pools, so you can be sure that, well, okay, not sure, but reasonably likely that you can allocate even if there's memory pressure and you're in an interrupt context. The next thing is, if you get below the thresholds, the watermarks, then it gets refilled automatically during reclaim. And yeah, that's about it. The bad things, well, it is static. The thing is, the zones are initialized before we even have discovered those devices. Like if they're on a bus that is enumerated, like PCI Express, then that happens much later than the zoning. And there can be only 3, normal, DMA32, and DMA. Some architectures don't even have all 3. And there can be different constraints if you have multiple buses. And we have seen systems where it's challenging to find a suitable DMA zone limit. So my idea, and this is like a very rough idea, and I'm really hoping that I get some feedback and someone just jumps up and say, why don't you? Instead of using these static zones, I would just create some allocation groups as needed. I'm not calling them zones because there are some differences, although you will recognize that some of the structures, like some of the features I'm describing here, would be contained in a struct zone these days. Maybe we will have to split the struct zone if we decide this is a good idea after all. Right. The thing is, when a device is registered, it is already known which limitations are in place, both the bus translation and the limitations of the device itself. So we can group devices that have the same constraints, and if there is no group that matches the constraints, we'll just allocate a new one. Good. Now, the difference is this kind of zone or allocation group needs to be populated somehow, which is different from populating the zone, and it's also not quite a reclaim. I mean, I call it initial reclaim in quotes, but it's not really a reclaim because there is no free list, and there is no RCU list, there is nothing. It's really like we have to somehow take away some pages from the normal zone. But once that is done, we can just treat it kind of like a zone. So when the body allocator finds out that, okay, we are below a watermark, it will automatically move from an RCU list into the free list, and it will be available with some sort of allocation, probably not get pages, but it probably will need either the group pointer or the device pointer or something that will just tell which constraints are needed. And yeah, if all goes really well, it could also automatically unencrypt those pages. So we could also get rid of these coherent pools and instead just rely on, okay, we have these emergency pools already built into the allocator. So that's just about it. Okay, I'll probably return here, and now do we have time for questions? Yeah, like jump up and say, why don't you just simply?
And so yeah, these groups would be somehow associated with the device, right? But not like completely reserved. So when no device needs them, would the normal allocations like be allowed to use them, or only movable allocations, or?
Yes, so the idea, thank you. So yes, the idea is only the emergency pools would be reserved, but all other memory would be movable into the normal zone.
The low memory reserve logic is pretty difficult to understand, and yeah. So would you then need to expand that to kind of, you'd have to expand that, I think. So that determines how much of an ordinary allocation can use a lower zone. So I guess, have you thought about that, or have you looked at that code?
Oh, the idea is we will not have zones. We will, okay, we will, because we will still have the normal zone and the movable zone, but we will not just, we will stop dividing memory by addresses. Like, forget it, that's obsolete.
That's pretty bold.
So in some sense, it sounds similar to CMA to me, which is kind of also, this is reserved, but movable allocations can use them and I can throw it away. But the aim is not to have large contiguous allocations, but allocations restricted to addresses that you need.
Yes, and also there's a difference. I don't really need a contiguous space. Like most allocations are relatively small, like order 1, order 2 maximum, and they can be sparsed. Like they can be like exactly. CMA is continuous, but this does not have to be.
How large are the ranges that the devices can use, like roughly?
What do you mean ranges? Like, what are the constraints usually? Like, okay. In general, there is no clear translation, like I explained, but I mean, you will not see a device that reasonably has less than 32 bits of address bits, certainly.
But I guess we wouldn't convert the whole applicable range to this CMA-like thing, because that would place constraints on normal allocation. So we were to decide how much to...
Okay, yeah, I get it. So the question was how much memory would be moved into such an device allocation group. That's a good question, and I don't have a good answer, because obviously it depends on how many devices share the group, and also depends on the kind of device, because some devices really only make a small allocation at initialization and never again.
Then you have video decoders.
Yeah, exactly, and then you have video decoders.
I think we'd also want to make them movable. So if kcompactd comes around and says, I want that page, I mean, it's free, right? So it's very easy to allocate a new page and say, yeah, I already freed the data out of that one because there's no data in it.
And I mean, for a blocking allocation, it's no problem to just get that memory back from the normal zone. Just really, the only thing I can imagine really makes a difference are these emergency pools with GFP atomic.
I wonder if we can enhance that further and integrate it with the I've forgotten the name, but we have an individual per device driver cache that we can do for emergency allocations.
Yeah.
Mempools, that's right. So if we can integrate this with mempools.
Theoretically,
because right now the core MM has no visibility into individual mempools. So again, if kcompactd comes around and says, I would like that page, and it's in a mempool, it can't have it. So, but if this is if it's integrated into the MM,
you need the more device drivers to use mempools, because now it's only kind of tens of them maybe using mempools.
Yeah, I mean, I don't particularly enjoy the current mempool implementation, but if this can solve the same problem as mempools, and it kind of sounds from what you were saying like it might be able to. So if it's not just atomic allocations to get to use the emergency pools, but other things, this could be a real improvement for the kernel.
I haven't looked into mempools, and yeah, I know yeah, thank you. Like.
Okay, do you hear me? Yep. So thanks for attending this talk. So I'm SJ, and this time, last LSFMM, I have presented some status update and the future plans for discussion, and then I have failed at management of the time at the time, and therefore there was some questions or concerns that I was unable to address. So I'd like to handle such things today again. So first of all, as always, the opinions are on my own, and this talk is more focused on discussion rather than presentation, so it will not touch much of the internal of the Damon itself. So how much of you are knowing Damon? How many of you heard about Damon? I mean, not the movie star. Okay, so Damon has merged into the Linux kernel from 5.15, so it's a little bit young and small subsystem. So to introduce it again, Damon is a data access pattern snapshot generator, which informs you that which address range is how frequently accessed for how long time. And it currently supports virtual address space and the physical address space, but it can be expanded for some more special types of address space. And it is designed for low and controllable monitoring overhead and the easy extensions. And it supports a access-aware memory optimization engine feature called Demos. It allows users to specify which memory regions of which access pattern they have interest, and they want what kind of memory action to that. And currently being used in some kind of real world products, including AWS or Serverless V2 and SK Hynix HMSK. Yep. So my two long-term goals for Damon is making it to help kernel be more extensible and also be just work. So for making the Damon to help kernel that is more extensible, we are trying, my plan is to expose the Damon functionalities as much as possible using some stable but extensible user space interface or ABI. This is required from some of the kind of big tech companies who have confidence in knowing some more information, more than even kernel, and having a very good understanding about their workloads. And to expose the Damon functionality, we are currently using CCFS interface, which is on the syskernel Damon directory, and we are using the CCFS philosophy, which is generating one file per one data. And in the way, I believe that it can be more extensible for future extensions. It therefore would have many, many files inside the directory, and it already having many files, and it might make it not very easy to be used by users manually. But our intention is to provide the user space tool for manual users control of Damon. For that, I'm directly maintaining and developing the Damon user space tool, and we are striving to provide backward compatibility regardless of the version of the underlying kernel. And also, we are very open to some kind of integration of Damon with BPF for some more extensible control of Damon internal logics. And why we want to make Damon to help making the kernel that just works. That is, as I just mentioned, sometimes some users know many things about their workloads and also systems, even more than kernel, but that is not always the case. And therefore, we still need to make kernel to at least reasonably work well without such complex tunings or controls. For this, we will add Damon modules. That is, Damon is currently implemented as an in-kernel framework. That is, it provides API to other kernel components like modules or subsystems. And therefore, for some kind of more concrete and simple but common use case like proactive reclamation or proactive LRU list sorting, we are currently having the specific kernel modules for specific use case. Currently, we are providing modules for proactive reclamation and modules for proactive LRU list sorting. And also, we will continue adding more as we find more specific use case, especially in case of SK Hynix HMSDK. The CXL memory tiering could also be such a use case. And also, we will continue simplifying the user space ABI by adding more auto-tuning features that can replace the old CCFS files. That is, we will add more files, but the old files will continuously being rarely used and replaced by use of the new files. And eventually, in a long term, far future, we want to reduce the knobs one by one in this way, and eventually it should be one single knob that is one single kernel configuration. I have no idea about what the name of the configuration could be there, but say config Damon X. By setting this as yes, the system will utilize all the Damon-based system optimizations at once by default. Of course, the configuration will be no by default, but as time goes by, we can think about. So that's it. And any questions or comments would be very welcomed. If you have no idea about what question can be raised, just use this. As I presented too perfect.
Yeah, could we use this with the BPF thing to get like a trace of exactly where, like you generate a heat map and you tell us what is like very much accessed a lot or whatever, and then we could figure out the call path as to where it's getting accessed or where it was created. like kind of like tying into what Søren said earlier and John mentioned.
Yeah, it is available. Currently, the Damon's monitoring research can be collected using POF because it provides a trace point. So it exports the monitoring research using trace point, and if you can use POF, you can collect the data and then visualize the research in heat map-like thing. That's exactly what Damon user space tool is doing from user space. And also, as you just mentioned, we can also make some mappings from the memory regions to specific code using some additional information that I believe that is not necessarily need to be done by Damon itself, but we can use some different tracing tools like BPF trace, POF, or whatever. And actually, that's already integrated inside the Damon user space tool. The Damon user space tool collects not only Damon monitoring research, but also some additional information such as memory usage and memory mapping information and the hotspot of the code using POF and BMstat or MEMinfo. And therefore, I think such information can be generated. And we are providing the feature with Damon user space tool because the Damon can. So my basic intention of Damon is making system that just works but also extensible in some each way, but in some case, some people would want to do some kind of profiling guide optimization-like thing. For that, Damon user space tool is currently being developed in the way to support that, easy way.
So maybe I have a question about the sysfs interface. So I believe the rule is it's a single value per file. If you are providing more complex data, then it should be the BuckFS. So maybe that's the answer to that question.
Yeah, as you just mentioned, for more complex but human-friendly output representation, debugfs or procfs would be the right approach. But I also have no real good idea about how Damon will be evolved. We are trying to use just random evolution more than intellectual design. And yeah, so I think that could be extended much more than I can imagine at the moment. And therefore, I believe that the sysfs interface is might be a better approach for long-term stableness.
Does Damon actually support working in the VM right now? Or it only supports working on the host?
Yeah, you can run Damon for monitoring access pattern of virtual machines from host side. And of course, you can run Damon inside the guest, whatever you want. Yeah.
Yeah, by the way, we didn't say to the remote speakers, if you want to ask a question, then either turn your camera on or use the raise hand so we know to tell you to speak.
Yes. Can you please, Mike?
So SJ, for the kernel that just works idea, is this basically the doing proactive reclaim? Like what is Damon actually going to be doing in the just works? Is it proactive reclaim to reduce unused memory and all that kind of thing?
So each open question. So for now, we are providing the proactive reclamation, and we will continue getting more that kind of purpose optimized kernel modules that using Damon for assisting the system. So maybe we can add memory tiering and also THP optimization, and some more things could be added there. And I was saying about the access contiguity aware memory auto-scaling in last LSFMM, and such a things could be added. And by turning this config Damon X on, it will find the system's configuration if it has CXL memory or not, and based on such a things, all the features that could be reasonably be benefit can be turned on.
Okay, so it'll look at your system and see where it can be useful, and then it will enable those bits. All right. Yeah.
And even after introducing the config Damon X, we might add some more such features.
I have another question. So is there any plan for Damon to integrate with PSI, for example, conduct some like PSI-driven reclamation?
Yeah,
Because,
exactly.
on your slides, I saw it's like fixed for 2 minutes right now. So I was wondering if you can have some fine control of how much amount of CPU cycles you spend on scanning. Like that would be probably more ideal.
You're correct. And it already providing a kind of auto-tuning that tunes the aggressiveness of Damon-based operations based on the PSI. Currently, some memory pressure store information value can be used as a target goal of the auto-tuning. As user set, if user set that goal, then the auto-tuning will just tune Damon on its own to meet the targeted value of the PSI.
There you go.
Yeah, I have a question, but more like the downstream part of the Damon. Like we have the Damon has all the data there, and some using it as a decision making. Do you think like if we could add some plugin there to analyze this data somehow? I'm just wondering, like from your perspective, this should be something from Damon. It is more from the consumer side thing, or you actually thinking about that?
Yeah, currently we provide trace point. It can be used. It also provides the snapshot in some efficient way using CSFS. And also in future, we might be able to integrate BPF so that you can run your analysis code written in BPF inside the Damon.
Thank you.
Okay. I'd like to talk about guard pages. So guard pages are something of an overloaded term. In this context, it's pages that if userland touches them, it generates a fatal signal, and it's something that will be set up by userland. This is typically used by things like a userland allocator or a pthread implementation, where you don't want a buffer overrunning from one thread into another thread's memory. And the way this is set up is the user will mmap regions of memory with prot none set, which means when the fault occurs in that region of memory, the fault handler will look at the VMA, see that it doesn't have access, and then cause a fatal signal. The problem with this is that you end up splitting up memory ranges and having to generate a whole bunch of VMAs. And if you have a large number of threads and a large number of processes, that can add up pretty quickly. And also, you can no longer merge adjacent VMAs that you otherwise would be able to. So this is something that people have actually hit in reality. So it's not a theoretical problem. And it takes longer to deal with a larger number of VMAs. So we've proposed a solution to this, which is to take this faulting behavior and take it away from the VMA itself, and instead put it in the page tables. And doing this by setting the PTE to have a non-present, non-swap entry, that's handled by the swap logic, that uses a PTE marker, which is a technique that's used by actually user fault FD. They have a similar kind of mechanism for simulating hardware memory faults. And then all that does basically is causes the fault handler to say, okay, a fatal signal should arise. And the advantage of doing this is you don't need any additional VMAs whatsoever. And then all of these problems that we've been talking about go away. So the way we've implemented this is via an Madvise call, where you specify a range via an Madvise. This Madvise guard poison to establish the range. So we sort of characterize this as poisoning a memory range. And then also something that is very much unlike the other forms of poisoning, where you can undo that operation. We call that remedy. And one very nice thing with the way this works as well is that when you do the reverse operation, if there's any memory mapped in that range that's not poison markers, it's just left alone. So you can install these poison markers and then safely say, I want every poison marker in that range removed. And then you can just do it with one call and nothing else gets touched. We've implemented a prototype and we've been testing that. Oh, and one thing to add, you can also use the vector form of Madvise, process Madvise to set up poison markers in one operation with an IOVEC, which is pretty efficient. So we've done a prototype and the results have been pretty good. In terms of time spent with these sort of mapping calls, it's like 5 times faster because you're just not having to do anywhere near as much. And on a idle Android system, unoptimized really for this, but with some changes, so the pthread implementation uses this approach. We've seen 13% fewer VMAs, which actually is a pretty big number considering that. With further optimization, it could be considerably more. So I've also now, we've only got 2 slides, so we're opening this up for discussion more than anything. So I've now got a series ready for RFC. That will be coming soon. I was waiting till this talk.
I just want to understand these guards. Do you have to put them in existing VMAs, or are they at the end of VMAs?
You have to put them in existing VMAs.
Okay, all right.
And so they essentially they remain part of the VMA, and then if you split or modify the parameter, split or merge or whatever, it will still stay with whatever VMA is associated with that range. If you unmap it, it gets removed. So that simplifies things. Okay. But it does mean that if you want to have a range, you have to kind of extend the VMA a little bit further.
So the idea is it stops you, or it helps prevent you accidentally running out of your VMA. It kind of comes just before that.
Yeah. Or you may have like a whole. It may end up being a large VMA that contains multiple processes or threads.
And how would this work for like file-backed memory? Map a file.
Yeah. So we're simplifying things at this point. We're keeping it simple and keeping it anonymous only. But in future, there are things to think about with a file-backed and shared memory potentially. So for now, we're for the initial RFC, it's just going to be anonymous only.
I think that's too much of a limitation. There should be a good plan to handle file-backed memory.
Well, I mean, the idea is that we can iterate on this. Yeah. So in future, we can expand what it can support.
Yeah, but then I just wonder what the semantics will be like. You know, if you're M-mapping a file, but then you need a bit of extra space for a guard as part of the same VMA.
Yeah, with file, there's definitely complications.
So when you say anon, do you mean just anon, or if you do anon and shared, which we know is magically transformed into being backed by Shemem?
Yeah.
Is that supported or not?
No, it is purely just a no Shemem at all. This is just for the first iteration. Obviously, we probably want to expand it going forward.
Yeah, just two quick questions. For the architecture support, adding a PTE bit, is that only needed in the non-present case?
No, this should work across architectures. It's, I mean, actually, what do you mean?
So I'm just worried because we're running short on bits in the page table entries.
Oh, no, yeah, there's no extra bit.
Okay, good.
Yeah. So
that's what I thought, right. Okay,
so basically, it's like a swap entry, but then you set a field to say it's PT marker, and then you use a part of that to say which PT marker that's.
Okay. And then the second thing is, what's the get user pages behavior on one of these?
Interesting. It would fail. Actually, the get user for something like populate, it would just result in an error.
Okay.
Yeah, because it does specifically check for that. It's good that I wrote the code for this, so I know that.
So today you can sort of already do this. User Vault FD has UFFDIO Poison, which installs.
I'm aware of it.
Right. So is the behavior that you want the same as that, or do you want like a different kind of poison?
Yeah, it's different. Firstly, that simulates hardware poisoning only, all right? And then you're going to get unwanted behavior. For instance, if you have config memory failure, you're going to have a ton of things in DMS, and the fault handler is going to treat it like a hardware memory fault. Also, I'm not sure on the reverse operation and the semantics of that.
MNV don't need would reverse the hardware.
We don't actually necessarily want the don't need to reverse, because that would be kind of unexpected.
You probably want to avoid that too.
And actually, in the RFC implementation on don't need, we don't get rid of poison markers, they stay.
So you make a new PT marker for your poison versus the UFDO. Okay.
Yeah.
Cool. Thanks.
And the reason for not using user fault FDs because it is additional overhead, and if you mark VMA part of it user fault FD, it leads to splitting, and so this should be very.
Hi, I was just, so I didn't see the RFC on the mailing list.
It's not up there yet.
Oh, okay.
It'll be there soon.
I was just gonna say, you commented that it's vectorized. Did I get that right?
There's the process Madvise call. You can. It needs some modification, actually, for it to be useful, which I'm gonna upstream as well.
Okay, and I was just gonna comment that I think that's really dope. I actually think that it ties in. I looked ahead in the schedule. There's another talk coming up next about Madvise, like a lazy don't need or lazy free. And there, a very long time ago, I saw an RFC get posted. I think it was like Kernel 4.19 or something like that. A very long time ago, somebody posted an RFC for a vectorized Madvise system call that would allow you to do lots of different Madvise operations, but with just vectors of addresses and ranges to effect at once to minimize like the amount of overhead for processing all of those at once.
Yeah, I mean, this exists, but the current implementation is designed for other processes, things like userland reclaim, out of memory code. So that needs adapting in order to use it on the same process, but that currently exists. It's not very well known, I don't think. Process _Madvise. Cool. So we're just going to adapt that to make it so you can do the same thing on the same process.
Yeah, no, I'm familiar with the system call. I just meant that I think it's cool that you're taking that approach for this, and I hope in the next talk to ask basically exactly the same question about vectorized Madvise V for reducing the number of TLB shootdowns, because vectorizing Madvise calls for presumably this use case is for setting up guard areas for VMs or something like that. I don't know exactly what you're using it for, but that's what I would guess, something like that. And being able to unmap all of those without generating TLB flushes or being able to generate the mappings with just a huge vector up front with a fewer number of calls, like both of those things I think are related and would be really dope to be able to do vectorized.
Cool.
Can you hear me? Oh, Lorenzo.
Hi.
Naming is hard, and you knew this question would pop up.
Oh, come on.
Can we at least poison? Using poison just sucks. But if you're gonna call it poison, can we call it unpoison, not remedy? Or just like something.
We have a certain sentimental attachment to these names, but I compromised. So David objected in the past in discussion, but each of these have guard _Madvise guard poison, Madvise guard remedy. So it's pretty clear what it's referring to.
Can you? I'm a native speaker. Why not unpoison? Why remedy? I'm just curious because to me it doesn't make sense, but I assume it makes sense to you.
Lorenzo, you can actually pull up a YouTube video if you need to demonstrate to David why it's
have you ever listened to the Prodigy?
Should I do that?
I'll send you a YouTube link and you'll understand.
Okay, if it takes a YouTube video, maybe unpoison. Just saying.
We could have maybe both.
So hey Lorenzo. So I'm really curious about the SIG-bus versus SIG-SegV question. I don't know what the right answer is, and I'm curious if anyone has any ideas.
I kind of listed a few possible things that may come up in discussion anyway on the list anyway. But right now, like the memory, like the UFFD poisoning will result in a SIG-bus, but I would argue a segment fault probably makes more sense in this case, but it's a little bit debatable. At the moment, the RFC uses a segment fault.
I would say it should be the same as if there were no VMA there.
Right. That makes sense, yeah.
Am I making the correct assumption that if you poison and then unpoison or remedy a page, the contents are discarded?
Yep. Yeah, so if there's any contents on poison, it's zapped or it's removed.
Does that mean like the page is freed and then you must allocate a new page to unpoison?
No, when you remedy, it will unpoison. it will clear the entry, and then when you next fault, it would allocate. It would do the same thing as if you just mapped a range. So if it's read, it would be to the 0 page. If it's write, it will allocate a page. And it's all anonymous memory at this point. So that's all we think about right now.
The reason why unpoison is, or remedy is the wrong word, right? Because you don't get your data back. So.
Wow. I feel like you've been chatting with David.
Why not do something like how mprotect prot none? You can undo that and get your data back. Why not do something?
But then you'd have the VMA. You get a new VMA, which we're trying to avoid.
So there's no way to do something close to prot none without having to have a separate VMA?
No. But so that's kind of the whole goal.
So the reason we cannot keep the data is because then we would have to still have the PFN in the PTE and then proc none, and then that's too many interpretations. Like NUMA balancing uses that, so the marker is the simplest way, but then you need to discard the data.
Thank you.
So the next speaker is remote. Hopefully everything will work.
Let's give this a try. Can you guys hear me?
Can you control the slides?
Okay.
Make yourself presenter.
Yeah, looks like it.
Okay.
I have way too many slides because I have a feeling what you guys would be asking, what questions you guys will be asking if I did not have any. So I'll try to zoom through the slides and leave some time for discussion. One thing we have noticed in our fleet is that we spend way too much CPU time on things like Madvise don't need and Madvise free. And the CPU time is not in the Madvise code itself, but it's in the TLB flushes. In the calling thread, about half of the CPU time is spent just flushing the TLB and waiting for other CPUs to flush their TLBs. And once you add in the amount of time the other CPUs spend flushing their TLBs, almost all the time spent in Madvise don't need or Madvise free is just spent doing TLB flushes. And this is on systems with a modest number of CPUs. New systems have more CPUs, and we expect things to just get worse over time. But we can draw inspiration from RCU in how we could solve this problem. RCU deals with overhead by first making data inaccessible, and then once all the users of the data have gone away over time, freeing the data becomes super cheap. And I think we could do a similar thing for Madvise don't need. I've been talking with the JE-malloc people for a while about what the user space API could look like. And it can be very simple, where user space indicates with Madvise lazy free, here's a range of memory that the kernel can free whenever it wants to. And it can call Madvise reuse to make a previously Madvise freed range available for reuse. This basically tells the kernel that it is no longer allowed to throw away any data that's written to that region after Madvise reuse has been called. The Madvise lazy free code itself will look fairly simple. First, we use the TLB gen number that we use for lazy TLB on x86 nowadays. We probably need to make that architecture independent. And inside the But remember that this range is getting lazy freed, so we stored it in a tree somewhere, and then we mark all the PTEs in that range as non-present. We could use a swap type like migration, or we could use PTE non, various ways we could do this. And that will keep other CPUs from loading anything in this address range into their TLBs. Madvise reuse is fairly simple as well. We would simply mark the PTEs as present again and remove the memory range from the tree. And there is no need to do any TLB flashes in Madvise reuse either. So when do we need to do flashes? We only need to do the TLB flashes if the memory is being reused for something else. That could either be the virtual memory being reused for something else by the application, or having the physical memory reused for something else when we free it, and then kernel is free to use it for anything else. But if there is a sufficient time gap between when Madvise lazy free is called and when we do the reuse, then some of the TLB flashes can just happen naturally at context switch time using the lazy TLB code. And we can reduce the number of IPIs that we have to send to other CPUs. And the context switching code, what the lazy TLB code does today, it checks whether the CPU's TLB generation number is smaller than the TLB generation for the MM. And if the CPU is behind, then we just flush the TLB. On x86, we do this today for the lazy TLB code. And this basically expands lazy TLB code to user space for Madvise lazy free, and we might be able to use it for other things as well. At reclaim time, this is where we have to check as well who still might have the TLB loaded for this page. So if we, at reclaim time, when we look at a page, we clear the page table entry, and then we have to iterate over the CPUs that have this MM loaded. It's the MM CPU mask on x86. I don't know what it's called on other architectures. At that point, we need to check if this CPU is still holding an older TLB gen than what is associated with this Madvise lazy free area. We need to send a TLB flush IPI. But if the CPU has already done the TLB flush by itself during a context switch, then we have to do absolutely nothing before we can free the page. And this is where I think we could save a lot of the overhead of TLB flushes. There's some optimizations we can do here. One of the things that I have code for right now is keeping a small buffer of flushed address ranges. And at context switch time, if we have a few small flushes pending, we can just catch up with those instead of doing full flushes. I tried this out with a web proxy workload without any Madvise 3 in there. And I saw about a 1 to 2% improvement in instructions per clock. But it only helps right now when the system has sufficient idle time, about 50% idle. That's when this code seems to have the sweet spot. So I didn't send this in yet, since it doesn't do anything when the system is busy. But I think with Madvise lazy free, this might be worthwhile. We might be able to use this kind of thing for munmap and maybe a few other things as well. Maybe we can also use it to solve the problem that Jungchul Park is working on with the lazy unmap flush. Some things we might be able to use some of this code for. And the lifetime rules for Madvise lazy free, we start on the upper left corner where we have a valid page table entry. If lazy free gets called, we mark the PTE as non-present, we increment the TLB generation. And then any of the other CPUs at context switch time can check whether their TLB generation is up to date or not. If it is not up to date, we do a flush. At reuse time, we don't have to do any TLB flushes. We just mark things as present again. And only at reclaim time, we have to check for CPUs that are not up to date and flush their TLBs. And I guess this slide is what I should leave up during the discussion. Does anybody have questions or comments?
He doesn't like the question.
Well, so my thinking is, like, can't you do something like an access bit? You clear the access bit, you still keep it there, and then later you can come and look and see if that access bit is clear or not to decide whether or not, whether you can reclaim it or not. Just the reuse.
MFVise 3 does that. However, it does mean that you need to catch every access that happens immediately after you clear the access bit. And that requires you send an immediate TLB flush. And that's the thing we want to avoid, since most of the overhead is in the TLB flushes.
Yeah, okay. The reuse, the need to do that reuse call just seems a bit cumbersome, that's all. From that.
It is cumbersome, but I think that most applications will never see it, because this is the kind of stuff that will be done by the malloc library or the runtime. So you see it in a jmalloc and a tcmalloc, and you might see it inside a JVM, something like that. But it's not something that most applications will ever have to deal with themselves. They just call malloc and free, and the library does all this stuff for them in the background.
Hi, thanks for the presentation. I was just wondering if you had seen code that was previously posted to the mailing list several years ago that was trying to solve a similar problem using a vectorized version of Madvise to reduce the number of IPIs that are generated for clearing, for using Madvise v, using don't need on a vector of ranges as opposed to just a single range. We use a version of that patch. So I work at a company called Fastly, and we use a version of that patch that I ported to a recent like 6.1 and 6.6 with some modifications so that we can do a fewer number of TLB flushes, but for a greater number of ranges, hence the question around the vectorized Madvise V. And I was wondering if you saw that old patch set from many years ago, and B, if there's a plan for lazy free to be vectorized so that you could unmap a large number of different regions simultaneously if needed.
I did see the vectorized patch. I don't remember why it never got merged upstream. I assume there are reasons for it, but I don't remember what it is right now. And I don't know if we need to vectorize this or not, because if we cut the overhead by 80 or 90% and the flushes are done asynchronously, then I think we get most of that benefit without having vectorizing in this particular call itself. Because once you flush the TLB, if your application does a number of these Madvise lazy free calls in a row, say 10 of them or 20 of them, and afterwards we do the TLB flushes, we'll still do only one flush to catch up a CPU with all of those Madvise lazy free calls. So you kind of get that batching for free without needing to explicitly vectorize it in user space.
Hi, Rick. This is David. Cool stuff. One question, is it relevant for your use case that during a reuse you get the same page with the same content as you would have had previously before you did a
No, that part really does. That part really doesn't matter. The application does not. At the time we call reuse, the application the memory might no longer be there. It might already have been reclaimed. The main
what I
thing that
was
reuse
wondering-
does is make sure that. Go ahead.
What I was wondering is if there would be a way that we do an Madvise lazy free, we mark the PT in a way, we move the page into a per process buffer list whatsoever, and whenever you want to reuse memory, we would simply take a page from the list, but we would just take any one, and if there's none, we would allocate one. Meaning that like it would be possible not to only get rid in the process of the TLB flush that you can defer, but also of repeated page zeroing. Like you have some kind of a buffer when you move pages and allocate them, that you can just reuse them like anywhere in your process if you have to reallocate with the semantics that you don't need zeroed out memory.
I think that's a really good idea. It solves an issue that some of the malloc library developers have been looking at, where programs free memory in a very fragmented way, and then malloc ends up allocating from a different virtual arena, and being able to just recycle these pages without zeroing in between could really help that.
That rely on the semantics of getting zeroed memory from their mmap.
There are applications that rely on Madvise, don't need returning zeroed memory. But in this case, I think we are looking at using it mostly through a malloc library, where the application calls malloc and free. And the application does not know whether malloc will give it memory that was previously zeroed or not.
Point, thank you. Unfortunately, time is up. Thanks, Fredrik.
Thank you.
Hello everybody. So my name is Kundan and I work for Samsung. And generally I work for Block.io, and this was the first time I delved into memory management. And yeah, this is a part of the Block.io which we will see today. So I'll be talking about transitioning get user pages to folio based mapping. And we have a sample implementation for it, and it is up for discussion. So we will see what is the current IO path looks like, and if we, with my sample implementation, how it looks like, and what happens after the conversion, what are the benefits of it. The current function call stack, how it looks, and then we will discuss about the solution, and also what are the challenges with this solution. So if we see the current IO path, the user space does a memory allocation. It can use a malloc, a map, or a map backed by huge pages, and then it passes the control to the kernel. The kernel does a page walk with the user space address using the process task struct, struct, and then using the user space address, it walks through the end of the page table and fetches the pages. So these pages, with the coming up of MTHP, these pages can be larger, and we can have larger folios instead of just 4K pages, generally what we have. And these pages, once are fetched, and they are added to Block.io and then submitted to NVMe. So with the proposed IO path, what we propose is, or what my sample implementation is we will have bigger folios getting returned as a part of page table walk. And once the bigger folios are returned, we'll directly add it to the Block.io. So I will first show you what the magic it did. So if we do enable MTHP with 128K size, and we give an IO of block size 128K, then the earlier ftrace function graph, which was taking 28 microseconds, started taking, with the newer sample implementation, it starts taking 3.75 microsecond, which is 87% of reduction. This was for the write IO. And yeah, so now let's see what is the current function call stack without the sample implementation. So here we see that we pass a pages array, and a page walk happens on that array. We go through all the levels of page table walk, and in the terminal function we take a reference on the folio, and this reference on the folio is taken for every 4K page, it is taken once. So if you say see 128K IO, it will be taking 32 times. And this part of code earlier was taking a reference on pages, and this got converted to folio. So now with my sample implementation, which I did, where I converted get user pages to get user folios based mapping. So instead of passing a folio pages array, which was passed earlier, I started passing a folio vec array. The idea for folio vec, I got it from bcachefs. It is getting used there. Because the folio size can be variable, we have to retrieve the size also. And that was one part. And then I changed the function signatures of all the function to accept a folio vec array instead of the pages array. The third thing what the sample implementation has is it checks for the copy on write. Like initially the folios can be contiguous, and we will have a larger folio which is directly mapped to the page table. But because of some reasons, it might be that one of the page got changed in between, and that's why we have to take care of, for contiguity, we have to take care of cow considerations. And then we take, in this sample implementation, we take a reference on the large folio, a folio vec only once. And once these things are done, and we get the folio vec array at the bio layer, we have to just add the folio vec array to the bio without any further processing. So that's what saves the time. So the challenges, I'll discuss two challenges. First challenge is if I change all the function prototypes to pass a folio vec array and NR folio vecs also, I'll pass these two are the new arguments, then there are several users of these functions already available. Do we intend to change all of them? So this was the challenge. And the second challenge is allocation of a folio vec array. So this is a performance path. And the moment we do extra allocation, which I am currently doing for a folio vec array, it will reduce the IOPS by about 9%, 10% for the at least 4K IO. So currently how it is handled is how the pages array is not allocated, and without allocation only the IOs proceed, is the pages array takes an offset from IO vec array of bio and then uses the same memory. And yeah, so that was one thing which was happening. And the second thing which was proposed by Hannes was can we use a folio batch approach where we have about 32 pointers on the stack, and then we fill the 32 pointers and it moves like that. So can we do like that? That will also avoid allocation. And or the other way is just have 32 pointers on the stack and then fill it. If the size of the IO is bigger than 32 pointers, then allocate a bigger chunk. So yeah, here recently I placed the sample implementation where I changed all the functions, and we have in this sample implementation we are changing the main function, the terminal functions where we fill the pages array, which was fast PT range and yeah, records of folios. So yeah, these were the part of the page table walk, the terminal functions what we changed, and pinning and unpinning I am doing only once for a folio vec. And yeah, so some part of these changes has been applied in the block IO part, but I did not change any page table walk functions as of now. So that's it from my side.
Well, more of a comment than a question. So you've correctly identified the problem, right? Which is that we currently take a ref count one at a time on the same folio over and over and over again, and that's slow. Absolutely, completely agree with you. That is something that we could optimize today. But I really don't like the approach you've taken. So converting everything over to use folios is a big disruptive change. Leaving we need, if we're going to do such a big disruptive change, I think we deserve a little bit more value for money than just this, because there are ways of getting. We could certainly do the amalgamation of getting the ref counts. We could actually do that without changing the API. The bigger change, the bigger benefit that I want to see, John and I had a good discussion earlier this conference. What we want to see is the ability to do I/O to memory which does not have a struct page. So that would be memory that is perhaps provided by a GPU or by a network card. I'm sorry? A virtual machine, yes. That's the other major use case, is that if you want to, Zen, for example, has the ability to do I/O to guest memory that it doesn't have a struct page for. So if you're using KVM, that is a disadvantage for KVM relative to Zen today. Yeah. So there's a lot of different benefits to being able to do that. So what we want to do is not get user folio, we want get user Fire, PHYR. We've had some discussion about this on the mailing list before. We have some starts at code. There's a lot of prerequisites, there's a lot of moving parts. This is probably a multi-year project, you know, a year or maybe 2 years. Sounds about right, John? 2 years, perhaps? There's nothing putting John on the spot. But yeah, I think we can. You had a slide where you talked about the number of microseconds per operation. Yeah, that one. That'll do. So we can do the mod node page state once per folio instead of once per page, but leave the API the same. I think that would be a great patch set. I think that would, so, you know, if you want to do that patch set, I will review it and we can merge that, absolutely. I just don't like your API.
Yeah, I agree. And yeah, as we have already done some part of the work, counting the number of pages once and then uploading it once rather than doing atomic additions again and again. So that will be a better change. Yes.
Great. Anyone else? Oh, David.
So I think there are many more optimizations we can do here. For example, like we have this batching of PTEs, we can make use of the contiguous bit and all of this. And I think these are all things we can do internally, but I agree with Willie that maybe we should keep the external interface as is for now, apply all of these optimizations internally, and then just like make up our minds, what should it actually look like? I assume there will be users that really only can deal with folios, like that they really only can work with folios. I assume, because not everybody wants to do DMA, for example. I cannot answer that, but my best guess would be that some people, they just want a folio, anonymous memory, I don't know. And for them, we could think of extending the interface if it's reasonable. But yeah, long term, we want something that just gives us something back. I'm just wondering, like with the fizzer, however you pronounce it, I'm getting most likely wrong. We would still like internally like take a reference if it's a folio, and it's just like if it's a PFN map, there is no folio, no reference, I assume.
So we determined that you always do need a ref count. The question is where is the ref count going to be? And so where the ref count is going to be will actually be abstracted away from the GUP code. The GUP code won't know where it is. The GUP code is going to ask the provider of the memory, where do I add n to, I've taken a reference on n of your, sorry, I've taken a pin on n of your pages. Please increment the appropriate counter.
Makes sense. And I mean, maybe you can just make like struct page so small that everything can have a struct page.
You know, I have thought about that, but so for a gigabyte of memory, it's, you know, even if you only have 8 bytes per struct page, that's still, you know, 256K times 8. That's, you know, it's
then you do the VMAP optimization. I
yeah,
just
yeah. Should we go for a break 1 minute early? Anyone? Anyone? All right.
Thanks, everyone.
People actually want to get like a PSN map, so you have to yet another one, and it's like the Swiss or however you pronounce it is getting closer to real. It's more like if like why add yet another intermediate one if you actually extraction? Is it a folio or something that's not? That makes sense to me. That was what you're saying. Like if there's like real performance benefit in there, we can show like in the folio interface. All of the other stuff that you must have talked about is like internal optimization. Yeah. I mean, performance atomics, patch it's just like let's not add another intermediate one if we already know that we're going to need something.
Right now, there's nothing to send. My session is the swap entry one, the swap allocator. So. Yeah, MPG. Oh, just like that?
Yeah, that's all of it.
Oh, okay, cool. The default fonts are too small.
Yeah, a bit. I mean, you can. No, then you don't have the mic.
Okay, yeah. Maybe you want to exit from it.
wonder if we have the correct chat now, but
Well, he said it was the right one.
Ray, so maybe it was the correct chat.
This is from last year.
Ah, yeah.
I remember that.
Oh.
Perfect.
Maybe sightseeing, maybe, I don't know. Sightseeing and name, opera. I won't go. But I think it was okay this year. And the larger crowd was also okay. 700 plus. It didn't feel too crowded, I think. Yeah. Because it's a big place and you still bump into people, so. There was huge demand after we've been sold out.
Yeah, if you have to do it in the kernel.
Thank you.
Okay. That's good to know. I will keep it further back.
So I did a new download, so hopefully it's the new one.
Oh, you couldn't download it?
No, he
Oh,
did
yeah.
it.
Oh, I had some troubles, but the website wouldn't load, but then I managed.
Oh, thank you. 1 minute.
No, it's time, no?
Oh, yeah, now it's 5 p.m. Yeah.
Okay, it's time to start our second half of the micro conference. So welcome back, and the first is ongoing challenges of large page sizes.
So, hello, my name is Juan, and my teammate Kalesh. So we are going to be talking about the challenges that we have found with 16K page sizes and more. So just to give you a little bit of background, it's like we are bringing up Pixel devices and Android devices with 16K page sizes, and then it's like right now we have 8 devices running with 16K page size, and then we found several issues, right? So one of the issues that we have found is with the CMA allocator. So what it was happening is like when we started bringing up the device, we realized that several hardware components that were not working, like for example, fingerprint, face unlock, they were not working. And the reason that they were not working is because it was not possible to allocate the CMA memory. And then it's like after doing some digging, it's like basically it's like the CMA allocator specifies some constraints, right? So when you want to reserve CMA memory, you have to have a certain alignment, right? And basically you have to have the CMA mean alignment, right? Bytes. So for 4K page sizes, this alignment has to be 4 megs. But for 16K page sizes, the alignment has to be 32 megs. But it turns out that like these hardware components, like the fingerprint, face unlock, they just require like 8 megabytes of memory. But in order to make it run in 16K page sizes, we need to reserve it. We need to set the size to 32 megs. So we don't know exactly why there is this constraint, like in the CMA allocator. And then basically it's like, we are looking for ideas like if we can relax these constraints, and if we relax these constraints, what are the advantages, what are the disadvantages? Because it's like we are wasting a lot of memory in devices where they are very constrained in memory, right? This is one of the issues that we have. And another of the issues that we have is with the prod locks. So it turns out that when we boot the device with 16K page sizes, the number of prod locks increased by 20 to 30%. And then we don't know exactly why we need more locks with 16K page size kernel. So it's something that we need to debug. So if somebody has an idea why this might be happening, why we require more number of locks, it's like we will appreciate it.
So another issue we faced when we are moving the Android ecosystem to so another issue we face when we are transitioning the ecosystem to use 16K page sizes is firstly we need to change the ELF segment alignment to be compatible with larger page sizes. And this okay, so here I just have a basic illustration of how the ELFs get loaded into the virtual memory. So for each segment, we align it up to the next page boundary, and we map it into different pages so that they can be loaded with different permissions, since generally the segments have different permissions. In a 16 KB segment aligned ELF on a 16 KB device is similar to what we have in 4K. We line up the segment size to the next page boundary and we map it into the reserved VA space. But the situation that we have on Android is we have existing devices, so 4 KB devices, which have the 16 KB aligned ELF segments. So in this case, when the loader maps in each segment, we round up the size to the next page boundary, we end up splitting the reserved VA space that we did to map in the ELF, and we end up with these extra prot non VMAs, like Lorenzo was saying, like these guard VMAs in between each segment. In this case, is a file backed. So there are like tens of thousands of these in Android. And this leads to the VMA area struct slab increase. It's the same thing. So there are a couple of options to fix this. One is we can unmap these prot-non VMAs, which has some overhead. And also on Android, we didn't choose to do this because the kernel can sometimes give you another mapping which exists in between, unrelated mapping which exists in between consecutive segments of the same ELF, which we found to be strange. So the approach we are taking is we extend the VMA, so similar to what Lorenzo's guard VMAs was doing. Earlier, the prot none area is included in the preceding VMA. The permissions are the same. In our case, we don't, it's not prot none anymore. There are some issues which arise because of this solution, and one with this.
Yeah, once that the extra VMA area was fixed, it's like we came with more issues, right? So basically, it's like the problem with that is like several developers, for some reason, it's like they read the cat, they read prot ID maps to get the memory region of the shared libraries, and then they try to read or write on these memory regions, but because they are no file back, what is happening is like the applications, they were getting sick boss, right? So the solution that we did is like to compile all the system libraries. We like separate loadable segments. So basically it's like what this flag does is add a padding at the end of every segment, and every segment is going to be a multiple of page size. So so what we achieve is like, oh, every part of the file right now is when we load the segments, they are going to be file back. So we are not going to get the sick boss. So yeah, we fixed that issue, but then it has this problem. The memory size increase and the file size increase, right? And the file size increases like because we were storing all these paddings in the file system, and also it's like when we were loading these like files, it's like the size of the page cache increase because it has to map these paddings, right? So what we did to solve that problem is like we made sure that we were using sparse files. So by selecting sparse files, in the file system, then the file it was smaller, and when the files were loaded, basically the read ahead was ignoring like all these paddings, and it was not allocating a page for those, right? But yeah, so basically it's like those are the issues that we were running into, and then.
So as one mentioned, when we have the ELF built with the separate loadable segments and we fold into the VMA, and since the VMA is extended to cover this padding region also to prevent the slab memory increase, what happens is in some of the file systems which implements a fault around, some application developers started to raise complaints that they have suddenly some RSS increase in their application. And this we found it was due when the fault around finds the pages in the page cache for the padding ranges, and it populates the PTE for these pages, then the RSS increase is visible to the user space application. So for the pages that were present in the page cache. So ideally we would like some way to, we have some out-of-street patch to ignore this padding region currently, but I think ideally if there was a way we could prevent the read ahead in the first place from happening in this region, the padding region, which we know we are never going to use.
So I think part of the problem here is going to be getting, we have all the information inside the kernel, we just don't have it all in the right place at the right time. So the file system knows where the sparse parts of the file are, but the flow is to allocate the page, then ask the file system to fill it. So that's no good. Readhead doesn't know. So the ELF loader knows where the regions are, but I wonder if we could have an API for the ELF loader could tell the page cache, hey, I know this is a hole. If anyone tries to read it, return the 0 page. Do you think that would be a good solution?
Yeah, that's what we're looking for. And yeah, as you mentioned in the L file, we already have in the header all this information, like where the segments are. So it's like, with that information, we can easily find out where the paddings are. So we don't care about the paddings.
Yeah. So perhaps I should ask a bigger question, which is anyone, I mean, literally anyone in the room, does anyone in the room have a use case other than this for, I want to handle sparse files more efficiently? I'm seeing, David has an example.
I'm sorry that I have to talk all of the time, but for RotoMM, there are use cases where you might have shared files among multiple processors, and you would actually want to catch access to holes. You wouldn't want to allocate memory. You would have to find a way to just give a SIG bus or whatever, similar to if it would be prot_none. But I don't want to use poison remedy. Unpoison. I don't want to like write to gigabytes of page table data just to say it's a hole. And ideally, if I'm in the main process, I can say, well, this is now like no longer a hole. I want it to just like work for everything. mshare might be a reasonable thing to do, but that would not be on the file level. It would be on the shared page table layout level.
So it sounds like you want something that's subtly different from what they want, because what they want is for reads to return zeros, and if it's M-maps, then they want the 0 page, and writes to it won't ever happen because, I mean, obviously it's VM exec, it's not writable anyway.
But do we really want a zeroed page? I mean, the shared 0 page is one thing that's going to be difficult. Do we actually not want to allocate memory on read? Is that what we want? Don't we want to allocate disk blocks on read? Is that what you're saying?
We wouldn't allocate disk blocks on read anyway. That's not something the file system would do. If you do a read to a hole in the file system, the semantic is that stays as a hole, and the file system calls memset in order to turn the page cache page into a 0 page, into a page full of zeros as opposed to being a 0 page. But it sounds like what you want is actually different. You want something that will fault if anyone tries to access that page.
Okay. Reading
Let's talk
0
about
is
that, not as part of this talk.
Reading zeros would be okay, but as soon as you would write and you could end up allocating disk blocks, then I don't want to waste memory. I don't want to give a process the ability to allocate ranges in a file that it's not supposed to touch.
Okay, let's continue that conversation.
Like fallocate would work, but not like using page faults.
Okay, all right, thanks. Does anyone else have? Oh, Hunt does. Good.
Just about this point, I would note that this is an existing problem because everybody who has any ARM64 binary that is not Android already has sparse files. The only reason why you noticed it is that it caused a regression for you. So it changed for you, but everybody else was already in the bad case. So if we optimize it, everybody benefits because Android was the only thing that had the 4K alignment on ARM64.
Okay, I think I have a solution that we can work to say this is a hole. We know it's a hole. Treat it as a hole. I think we're good.
And what David was saying, presumably the poison remedy feature would also have this problem if extended to far-backed VMAs, since it's in the, you still need the enclosing VMA for your.
So we have 1 minute left. So.
And in regards to the CMA allocator, does anybody knows why we have like these constraints about the alignment? Like because if we want to allocate just a megs of reserved memory in a 16K kernel, it's like we cannot do it. It's like we have to allocate 32 megs.
I think it's tied to how page blocks are sized based on max order. We would have to make them more granular for larger page sizes, I guess.
Because it's like for 64K page sizes, it's even like I think that it's 128 megabytes the alignment.
Right now, Power defines page block size different from max order, so ARM64 can just hook up to the same functionality.
So I guess we have to wrap up. Thank you.
Thank you.
Thank you.
Oh.
Okay, my name is Chris, and I'm going to present the MTHP and swap allocator together with my collaborator, Kai-Ray. Before I continue, I would like to see a raise of hands, and how many of you don't use swap at all? Please raise your hand. Okay, a couple of them. And how many of you that use memory compression-based swap like ZRAM, ZSwap? Whoa, about 40%. And how many of you use SSD swap? Oh, quite 30. And how many of you use hard drive swap, HDD swap? That's why I thought nobody wants to suffer. And yeah, that segue to another thing I want to ask for help first is that I have a theory that the current SSD swap is writing the pattern that the worst to the SSD in terms of like write amplifications, and I want to make optimization for that. But obviously, this is vendor specific, like how they choose their internal algorithms. I have some understanding of this, but my understanding might not be current. So I want to reach out to anybody who can reason the SSD internally, like how they do the erase block, garbage collections, and how they impact the write amplifications, and please reach out to me. I'm not going to go into the detail for that, it's quite complicated. And I just like shout out for help. Like if you are one of the vendors, you know these internals, or can provide suggestions on how we can choose the SSD swap locations, etc. A little bit about the background for the swap. I think probably you are familiar with the swap. And the swap is a swap file that provides location for the swap to write to. And it has limited size, obviously. And it also have different orders, or the swap entries you want to write to. Right now is very typical. It's 0 orders of 4K or 2 meg. The swap entry allocation, it's actually, if you look at the nature of this problem, it's a bin packing problem. You have a fixed size of the swap file, and then you have different orders of the swap entry. You want to maximum utilization of the swap file. So it's a bin packing. And there's some recent trends that we see on the swap file, as the raised hand we can already see. Previously, we designed the swap file systems is for hard drive or SSD. And now a lot of people moving to the compression-based swap, like ZRAM or ZSwap. And there's recently more like in the middle, like MTHP, like the different size between 4K and 2 meg as a swap entry allocations. And pretty much in Rome, nobody used hard drive swap. And the current swap allocator, it already used the cluster-based allocations, but it only does half of the job. It will allocate the location, but find the location, but the actual allocating and reserving the entry are done in the traditional hard drive allocation path. And with the, it's using one single list to link all the cluster together. And then for the hard drive allocation, which is the functions scan, swap, map, slots, and it's using a pre-allocated swap map array and doing a brute force kind of the scan to find one empty slot to use. And these have a quite complicated interaction with the try to allocate SSD swap. If you read the function, you will see a lot of go-tos inside them, and then the whole logic is fairly hard to untangle. And then one of the side effects that if you're allocating larger than 0, like the big swap entries, and you run out of the free swap
a list, and then you will pretty much always fail. So the failure rate is really high for that. And then here is our new cluster order-based swap entry allocator. So to writing of this swap allocator is actually not easy. It goes like this. You are not doing what I told you to do. You must you must unlearn what you have learned.
All right, I have to try.
No, try not. Do or do not. There's no try. So that's basically what it goes, and we completely dropped the old hard drive allocation, that big mess, and a lot of go-tos. And we use change the cluster allocation to use a double linked list for linking all the cluster together. And then we arrange many lists to manage those clusters. So that we have like the free cluster, obviously that was the entry that was not used, the cluster not used. And then we have the non-full cluster for each order. And also the fragmented cluster, which means that you try once and you won't able to allocate entry from it, but it's still not empty. And those we will try to reduce the attempt with repeating on those. And obviously you have the full cluster, you need to use that to reclaim your swap cache. And by using this, we can completely get rid of the whole global scale swap map scanning to find the swap entries. And also, it's easier to find swap entries. By doing this rewrite, you're actually providing opportunities for us to do more kind of optimizations. Oh, by the way, most of this is already on the Unstable and Linux Next. About like 1/3 of the patch is already on the list, and then there's about 2/3 still pending, haven't sent to the list yet. And then I'll hand over to Kyrui for the next other further optimizations we can do on the swap allocator.
Okay. Thank you, Chris. Yeah, this works. So another major improvement of the new swap allocator is that we can resolve the locking condition issue on the swap device by a lot. And one basic info is that there is currently 2 sets of locks. One is the SI lock, the swap info lock. It's a per device lock. It's a big lock, and its condition is heavy. So another one is a CI lock, the cluster info lock. It's a 1 lock per cluster, and 1 cluster is 2 megabits space on the swap device. So this lock is much smaller. And the previous allocator, it have always to grab the 2 locks because of the complex workload we mentioned before. And it have the typical locking order of the old cluster, old allocator is it have to acquire the SI lock first, then it acquire the CI lock, and that's due to some historical reason, and the SI lock condition will be very heavy. But now we have moved the allocator to operate completely on the units of the clusters, so we now have the chance and the motivation to just get rid of the SI lock usage as much as possible. And to do so, the first thing we do is we reduce the SI lock critical section. We just converted many things that used to be protected by SI lock into either lock list or or use just a different set of lock. And then we just reverse this to locking order to make it make much more sense. So we just grab the CI lock when we're operating on a cluster, and we do not touch the SI lock unless we need to. And the SI lock now will be just protecting the list, no longer protecting the clusters. And by this way, the new allocator will just operate on will just need to take the CI lock in most of the operations. And it will only need to take the SI lock when it need to move the clusters between the lists, because the SI lock not only protect the list. And because the cluster have up to 500 entries per cluster, so for example, on a freeing path, most of free slot on a full cluster, it have to be moved to a non-full list. That will require to acquire the SI lock. But the cluster will stay on the non-full list for a long time because it have many entries, like to more than 500 entries. So most freeings will do not need to take the SI lock at all. And because of that, on the freeing path, we just successfully get rid of the SI lock. And there's a thing called the sort cache. Now, the sort cache was just introduced years ago just to reduce the overhead overhead of retaking the SI lock. But if the SI lock condition is gone, we can just remove the sort cache for the freeing path as well. And for the allocation path, the story is similar. Each cluster have up to more than 500 entries. So most allocation do not need to change the cluster location. It will stay in the non-full list. And because we also remove the SI lock on the allocation path, so we can potentially also remove the sort cache for the allocation as well. The sort cache should serve as some marginal effects, like batching the update of some counters, but that can be optimized in other ways rather than using a very large cache for that. And by doing so, we'll have up to 10% performance gain for the typical usage. Okay, so here are some test results. So there is a
do we need to have the test results? We're supposed to be having a discussion, and we've got 4 minutes left. What are your questions to this audience?
Yeah. We can skip some. So anyway, so further, the result is looking better, and now there is one of the issue is we have a very high success rate for something out of the smaller clusters now. But for the larger clusters, it could, so a larger allocation, high order allocation, the successful rate is not as high as we expected to be good enough. Like for example, for the allocation smaller than 64 kilobits, we can have a success rate close to 100%. But as the allocation size goes larger, the success rate will be lower. Chris have some ideas, like we can reserve some part of the swap device to be only used by the large allocations, or we allow the swap house to use non-continuous slot for large folio. That's to propose to solve this issue for large allocations, but we are open to suggestions as well on this one.
So rephrase the question is that for allocating large order swap entries, currently there still have fragmentation issues for even we use using these cluster-based allocations. And then one way is just to reserve or dedicate certain cluster for certain orders, and then that can solve that issue. But I'm looking for suggestion, any other easy to achieve. That's fairly easy to do, but I'm open for other suggestions how we can get there without do a lot of rewrites. And using the non-contiguous swap entry is a lot harder one. It's a big overhaul due to the swap cache and stuff. That's a tough problem. Suggestions?
I have answered on previous question about SSD. So now we can use the NS SSD, but I think it's not something that we would like to use because you should write in append-only mode, and we have limited number of open active zones. But currently we have FDP SSD. Maybe it's something that you can consider because in this case you can provide hint to the device.
What was your question on the other SSD? I wasn't here.
Current technology provide zone namespace SSD and the NS SSD. In this case, you need to write only in append-only mode. But it's not something that you would like to use because I think you would like to update. And another, it's FDP, flexible data placement SSD. So it's something like more flexible. You can use as conventional SSD, or you can something like define hints and distribute your data between different reclamation units or something. So in this case, if it's the NS SSD, you don't need to care about garbage collector on SSD side.
I'll probably talk to you offline a little bit because I cannot pick certain words, like certain type of SSD, I did not get the word clear. So
I think I understand what the point being made, which was that if you're looking at a zoned device, then if you do a continuous write, which swap mostly is, right? If you're just appending, then when you get to the end of your device, you write back to the start, you find the ones which are still valid, and you garbage collect yourself rather than relying on the drive to do garbage collection for you.
That's what some of the ideas I have to make the modifications. Right now, the swap write is just random write for case. I think it's pretty bad. Yeah, that kind of the solution is actually what I'm looking for, and I have some idea how to do those things as well. Yeah. There's another like compound.
Yeah.
Kernel compound number is pretty good, but yeah.
Thank you.
So we are staying on the topic of swap and THP, but the next speaker is remote, so can you start, Barry?
Yes. Hello, this is Barry. I'm going to share with you the current status of THP swap out and swap in. And I'm also going to share some interesting user case after we enable THP swap out and swap in. So basically, I start from THP swap out, which is actually Chris and Kyrie have already introduced in the previous session. So basically, at the first beginning, only PMD map THP swap out could be swap out without splitting. Then Ryan extends to THP. But then we reported a fragmentation issue because in Ryan's case said we have to get an empty swap cluster even for MTHP whose size is much smaller than cluster. So basically, if a cluster is not empty, you can't get it for MTHP swap out, even you have a lot of free swap slots in the cluster. So in Kyrie and Chris approach, we can actually use non-empty cluster for MTHP swap out. So basically, after apply Kyrie and Chris test set, we find the situation has improved quite a lot. But eventually, for example, on a real phone, eventually after the phone has been running for a couple of hours, we still unlikely to get continuous swap slots for MTHP to swap out. But the situation has improved quite a lot. With creation and Kyrie's test set, we can actually absolutely work around the fragmentation issue by, for example, 2 JRAMs. One JRAM dedicated for small folio and the other one dedicated for large folio. This approach can, for example, make a small folio quarantine in one JRAM, and then the small folio won't spread in a larger JRAM. So large folio can always swap out successfully. But I'm not, so that's what we are using for workaround the depth fragmentation issue. Maybe, and Chris has introduced some other approach in his session just a minute ago. And then for THP swap-in, it's quite important to products like Android phone, because in a phone, more than, for example, 64 60% of anonymous memory could be in swap. So right now, do swap page, for example, do swap page only supports small folio swapping. So once a large folio is swapped out, we lose it forever. So somehow we have to like get the large folio back into swap page. So yeah, like Chuanhua and me have been working on this, especially on synchronous I/O devices, and we have got some headset matched previously in 6.11. For example, if we find a large folio in swap cache, then do swap page will map the large folio found in swap cache as a whole. And recently we have been also working on allocating and mapping MTHP into swap page, but for synchronous I/O devices, because we are Android engineers, we have only the environment to do the test on Android phone, and the Android phone is probably a quite common use case because we have millions of phones in the market. So, yeah, all the MTHP swapping depend on ZSwap is never enabled because ZSwap can't handle MTHP. Once ZSwap is ever enabled, a part of MTHP might be in ZSwap, and some other parts is in the backend swap devices. So we can't, MTHP swapping can't coexist with ZSwap. So that's probably the problem we need to fix in the ZSwap team. And nothing. Oh, so after we enable MTHP swap on, swap in, we have actually developed some interesting use case. Yes, yeah, for example, by us or by Intel, we actually observed interesting phenomena. For example, if we do compression and decompression using larger size, we can actually improve the compression ratio and also significantly reduce CPU consumption to do compression and decompression. For example, sometimes we saved 70% of CPU for like compression, decompression things. So that's why Tan Quan Zheng from Opus team has contributed a patch set which can make like this SMALOC and ZRAM to compress large objects and save large objects directly. For example, for a 64 kilobytes large folio, this folio can be compressed altogether as one object, and the object can be saved in ZSMALOC directly. But for example, for MTHP whose order is 5, then this folio might be saved as 2 ZSMALOC objects. So we don't have hardware engine to do compression and decompression. That's what we observed by using CPU to do compression and decompression. And using Intel IAA hardware engine, MGLRU contributed a patch set, which can, for example, utilize the multiple hardware threads to compress and decompress. And then they have observed like the DRAM write latency can improve 10 times, and the DRAM read latency can improve by 7 times. So it's an amazing use case. Yeah. And yeah, as I mentioned earlier, like MTSP swapping can't coexist with Z-swap. Now we are seeing Kanchala from Intel is working on bring up Z-swap swap out for MTSP, and his approach is iterating each subpage in a large folio and like compress and store each subpage one by one in ZSwap zpool. So actually, I wonder if it's possible also for ZSwap to do the same thing as we are doing in ZRAM. For example, if ZSwap can also save large objects, but not iterating each page, it might be better on performance, but yeah, maybe the first step we can start from iterating through each page one by one. But yeah, on the other hand, I haven't seen anybody working on MTHP swapping support in ZSwap. So likely we have to resolve this problem if we want to support both ZSwap and MTHP swapping together in the same system. So yeah, finally I have some open questions. Like yeah, as I mentioned earlier, we only support synchronous I/O devices. So after we move to like non-synchronous I/O devices, what's the prop size for MTHP swapping might become a crucial question to answer. For example, if we swap in a too large size, maybe we are going to do extra and unnecessary I/O. It can cause a huge rate latency. So we have already a lot of discussion in the mail list. For example, some people proposed adding per subpage rate ahead flag. For example, for each subpage, we have a rate ahead flag, and we can use rate ahead flag to determine the swapping size, or even determine if we are going to do MTHP swapping. And we have already tried to add a swapping enabled knob, which was obviously disliked by Willie and Christopher. And recently, I'm considering if we can reuse the existing read ahead knob, like page class, for swapping read ahead. We have already existing page cluster which can define the maximum size for swapping. So maybe we can combine page cluster and the MTSP enabled the CSFS control together to set the maximum size for MTSP swapping. I'm not sure if you guys would like it. And some other consideration is, from like Ryan's patch set, maybe we need to consider the hardware architecture. For example,
So Do we have the MGLRU speaker?
Yes, I'm here.
You presenter so you can start.
Excellent, thank you. Okay, so yeah, I'm Axel from Google. Presenting on just some updates around MGLRU, and also, I don't have 15 minutes of content. I'm hoping to collect feedback, the group's interest in this topic, right? So for anybody who hasn't been paying attention to this area, I'll briefly describe what MGLRU is. It's an alternative to the classic active and inactive LRUs. The basic idea is to split the lists up into multi-tier, multi-generational LRUs, roughly ordered by access recency. So each of these generations, which is a list of pages or folios these days, has a birth time stamp, which allows recency comparison across LRUs. So you can compare age from a file and a non-LRU, for example. One of its key selling points is to optimize aging and generation updates by efficiently forward scanning the page tables. So it's very cache friendly. And another big idea it has is to simplify reclaim between a non and file LRUs using a refault eviction based PID controller. So in terms of the current status of MGLRU, it was merged in 6.1, so almost 2 years ago now. Various major distros enable this by default, so Debian, Fedora, and Ubuntu. And within Google, we've adopted this by default in Android and Chrome OS as well. So one of the things I've been working on a lot lately is adopting this in the Google production fleet. So historically, Google ran this thing called KSTLD for time-based proactive aging and reclaim. The idea is it scans memory periodically. It keeps track of which pages have been accessed. It scans in physical page order with RMAP lookups, so it's very cache unfriendly. So kind of as a first step to transitioning to MGLRU, we added a small wrapper around it so it can sort of emulate some of the KSTLD interfaces. We extended it to allow periodic aging. So normally MGLRU will only do aging and look at the access bit when it needs to, sort of at eviction time, for example. We changed it so you can say on a fixed interval every couple of minutes, go ahead and scan and create a new generation. And then we extended it so you can say reclaim everything older than a certain time. So this kind of shim around MGLRU is running in Google production today, at least a fraction of it. And so far the results have been great. We got the same memory savings we were getting with KSTLD with vastly less CPU overhead, like 5x less CPU overhead. One of the other things we've been working on is extending it with to scan KDM's MMU secondary page tables. So we can do working set reporting and proactive reclaim for VMs as well. One of the important things this series also does is it makes the scan lockless. So this drastically reduces KDM MMU lock latency or lock contention. So I have a link here to the patch series. This is James Houghton's work on the mailing list. And then the lock contention benchmark, that was something Yu Zhao posted in an earlier version. So kind of one of the things I want to do in this talk is just collect what are some of the lingering problems or use cases that are not addressed that are sort of blockers for adopting MGLRU in more places. There are a couple things we know about. There's been some discussion on the mailing list where you can get killed too early if writeback falls behind. For example, if you're in a memory constrained C group and you're writing to a slow IO device. So there's a fix posted upstream for this. Basically, the idea is when we go to scan and we find all the pages are dirty, we wake up the flushers. I think this does fix the issue at hand, but there's some lingering areas of improvement that can be done here. One is just smarter decisions about when to wake up. Another is smarter throttling, or also just deciding who's in charge of throttling right back, right? I've heard some people say, well, the person doing the wake ups should be the one to not wake up and throttle in that sense. Or there's the cgroup level right back throttling we have as well. Kind of another constraint is today MGLRU has these dependencies in kconfig, so you can only enable it on 64-bit systems, for example. The basic problem here is lack of page flags. MGLRU needs at least 3 bits. So a proposal here to free up some bits to enable it even on 32-bit is to put some of the bits in the LRU pointer low bits. We think page active and page unevictable are great candidates for that, and possibly page swap backed. And then, yeah, I'm interested to hear any problems the audience has. So problems or bugs is one side of it, but the other side of it is just supporting different use cases. So one big use case, MGLRU, as it sits in the upstream kernel today, doesn't kind of address is proactive reclaim and aging, like I was talking about. So the sort of KSTLD emulation thing I mentioned isn't really the best interface. It's not maybe what upstream would like. Really, the purpose of it is to match Google's existing stuff. But we have Yuanshu has been working on this series upstream, which we think is a much better interface for this. His working set reporting series. So this does some similar things, right? It generalizes the active and inactive counts to arbitrary time intervals, so you can for a given amount of coldness time reclaim those pages. It gives you per cgroup, per NUMA node, and then per type of memory working set information. And he's working also on benchmarks that kind of show the usefulness of concrete data, and then also interested in ballooning for VMs. That's another area where we think proactive reclaim could be pretty useful. Another idea is just the MGLRU and the reclaim path generally is full of a lot of heuristics. These heuristics may not be perfect for all workloads or all use cases. So there's an idea that perhaps some of this can be implemented in BPF. That way you can customize it if you have a workload or use case that's not, properly addressed by MGLRU out of the box. We think that kind of an extension would be especially useful for other hyperscalers besides Google to adopt MGLRU, since they have may have pretty particular requirements. So yeah, for the last 7 minutes we've got, I was hoping for some discussion. If anybody has any questions or you have problems with MGLRU, let me know.
Thank you. Yeah, I don't know if you caught the talk earlier, but there was a talk by the author of Damon, and I see some overlap here, like specifically around things like proactive reclaim and working set size reporting. I'm keen to know what are the similarities and differences, and if somebody wants to get working set size information, which tool should they use and why? Yeah, and maybe SJ, you can also comment on this.
Yeah, for sure.
Please go ahead.
Yeah, so when we were doing this, we did evaluate both multi-gen LRU and Damon, kind of to see which one would be a better solution for us. I think in the end, we went with MGLRU just because it matched better our existing way of doing things. I think also Wei is on the call here, and he did the evaluation. He could provide a lot more details. Sorry to throw him under the bus. Or Sanjay, if you have comments about that.
This is Wei. So I think at that time when we did the evaluation, one of the main feature we were looking at, which is supported much better by multi-gen, is that we are doing the system-wide monitoring. So because we are interested in, say, swap out code memory to save memory cost from a system perspective. But I think at that point, demo is a lot more focused on process level view of page height and the code information. Basically, that's basically much different granularity, which we don't deal with at that time. So another thing is that for us is that because multi-gen as a new LRU replacement, we're going to deploy that in a fleet so that getting the working set information now become like just additional interface wrapped around that, so that we don't have to do like a page table scanning like in two different kind of contexts. There's also like some kind of interaction problems there. So I think probably still need to be sorted out. So basically, the cost perspective, that's another angle can be considered. The third angle here is that the multi-gen, the working set information actually is integrated well with LRU itself. Basically, if we want to leverage the working set information to do the reclaim, the page reclaim actually will be consistent with what we see from working set reporting. But with Damon, I think all of this structure managed separately. I think there's a lower level integration for our use cases. I think that kind of, at least I shared my what we are thinking, and I think people we have different opinions on this matter. I would like to hear, the people's thoughts as well.
Sorry, I didn't catch the question. For some reason, the audio from the room wasn't coming through for me.
I didn't catch that.
There we go.
Yeah. Do you have any roadmap for MGLRU to replace the traditional LRU so we don't have two different LRU implementations?
Yeah, I don't know about a concrete roadmap. I think basically getting rid of the active inactive LRU requires figuring out everybody who isn't supported by MGLRU and fixing all of those issues. I think an easier lift is probably setting it as the default in kconfig. I mean, because of course folks can always change that if they see fit, but that might help at least move some users over who just, like, there may be a subset of users who just have not been paying attention and don't have a strong feeling, right? So maybe setting the default can help with that, but yeah, that's kind of my goal here. I think the first step is to identify all of the gaps, so then we can work on fixing them.
I think basically just to kind of add on or repeat what Axel just mentioned, there's a known problem slide, and then the second bullet point of this new use case slide. I think it probably will be required for us to reach that state, basically, to have only one, at least a kernel implementation.
Yeah, I mean, if there's anybody else who, inside your organization or at your distro that you work on or anything like that, if you haven't adopted MGLRU, I'd be curious to know why, like what's missing, what can we do to support your use case properly? But yeah.
So the next speaker should be Yuzhao, also remotely. So I made you presenter and you can start.
Thank you. Good evening, everyone. In this session, we're going to talk about the page allocator optimizations for transparent heap pages, as well as memory partitioning. So I'll start with the first topic in the first half of this session, because we got a half an hour, and I might be able to, I might run over a little bit, over time a little bit. So if you have questions, please just stop me and ask me. I know it might be late for you, so I'll try to finish early for this entire session. So this was a topic at the LSF this year, and I reused most of the slides I presented there. Also, I added some new slides at the end of this deck. So here we are some facts why different architectures explored larger base page sizes, and of course on x86 we don't have that luxury, because the only base page size we support is 4 KB, right? So I have a proposition here. So 4 KB on at least on x86 was came out a long time ago, right? Probably 3-4 decades ago, and whether it made sense at that time, I don't know. But at the moment, I don't think that's the best page size for a majority workloads in data centers, not even on high-end desktop workloads or phones. So my proposition here is that OS should find a way to support larger page sizes or fewer larger page sizes over 4 KB, but at the same time, this feature should not depend on hardware or break ABI. Because, for example, on ARM64, if we want to switch from 4K to 16K, we would break ABI, right? So, but on x86, we don't have 16K base page support. Also, we don't really want break ABI. So that would be two requirements that can help us transition to a larger logical page size. So I'm not talking about any specific OS. Windows, Mac OS already has been doing this, right? So this is, I think, is a general true for most modern operating systems, right? Probably not embedded operating systems, but for most modern ones running on high-end devices, yes, I think this should be considered. So the rationale behind that proposition is that favoring larger page sizes can bring better overall performance, right? And also less metadata overhead. Because to manage, let's say I have a laptop equipped with 4 gig memory. So that would be, if I use 4K as base page size, that'd be 1 million pages to manage, right? It's not scalable. So also, since we don't want to break ABI, we still have to support 4K. So what does this mean for us, right? So that means you have to choose which one really you want to prioritize. Right now, we do support transparent heap pages, but they are the second-class citizen, right? Or at least, if you might not be able to get a THP, but even you can get a 4K page, right? So, but can we really make this the other way around? Can we say, okay, if you try to allocate 4K, you might fail, but if you try to allocate THP, you might have better luck, right? Just like how we support DMA and DMA32 zones. Let's say you have a really legacy device, you want to allocate memory for this device, you might fail, right? But if you have newer PCIe devices, you can succeed actually. So that means we have to look at the priority of allocating 4KB and THPs differently, right? So this is this different angle or this different point of view gives us this comparison table. Basically, right now, if we try to allocate 4KB, is cheap, right? We try to allocate THP is expensive. So the proposition is that based on the proposition, we want to make the opposite, right? When you try to allocate 4KB pages, you're going to be very expensive or relatively expensive. Or when you allocate THPs, they're going to be cheap, right? Similarly, when you convert between THPs and 4K pages or base pages, right? Why do we need conversion? Because without it, we would become a larger base page size, right? We would not be able to maintain the ABI. So that's why we must have the conversion. Right now, if we convert a THP to 4K pages, what we do is it's cheap, right? Because you just need to split this larger THP, 2 meg THP, for example, 2 meg THP into 512 4K pages. And but we actually can make it expensive, right? Because we say, okay, you are not supposed to. Let's say you are buying wholesale, right? You are buying a 6-pack beer, right? It's cheaper. But if you buy 6 bottles individually, the total cost might be higher, right? So that's the idea behind this. Also, when you convert a bunch of 4K pages into THP, right now it's expensive, but we actually can, in theory at least, to make it cheap. So here in this slide, it shows how we can do that, right? Because there are 2 ways to do the conversion. One is in place. I say if you, a simple example is that when you split THP, right, you do it in place. You do not make copy. You do not migrate data, or you do not make do not do copy, right? Do not copy data, right? The other one is out of place, right? So out of place definitely is like has an overhead from copying, right? So when you convert the 4K pages, 512 4K pages into THP, right? If you do the in place, we call it recover. This is something new, right? Right now we only have collapsing. That means you have to copy 512 4K pages into a new THP. This THP, this 2 meg THP is newly allocated. It's from different region, right? Also, when you do when you convert a THP to 4K pages, this new conversion shader is actually does it out of place. Right now, we don't do it in place, right? When you split a 2 meg THP into 4K pages, you just split, you just only change the metadata, right? You don't really copy the payload. But here, if you copy the payload to a new location, then you're gonna make the cost. You're gonna introduce a new overhead. But that's what I actually want to do. Why? Because as I mentioned previously, right, we want to make it expensive, because you're not supposed to use 4K pages, or 4K, we consider 4K pages legacy. You're supposed to use as many THPs as possible so that it can reduce the overhead and improve performance. Questions so far? Okay, good. Thank you. So the next in this slide, all I'm saying is that there are ways to implement policies or implement allocation fallback based on allocation time hints. Right? Right now we only have 2 allocation time hints, which are movable, whether this allocation is movable or not, and whether this allocation is compound page or not. Right? So of course, for some current allocations, we still use non-compound large pages or large folios, or not folios, non-compound allocations. So if we assign different weights to these two hints, right, then we can calculate how we should do the fallback, right? Here, JFP movable has base weight 2, right, and JFP compound has base weight 1. Why? Because if it's movable, right, you can move this allocation to somewhere else to make space for a compound allocation, right? So that's why it's movable is more important than compound. So by sum the base weight, right, you got total weight. So we can see here, I have a list at bottom. So movable compound actually is the most desired allocations, right? Because first you are you allocate other THP or large folio, right? And second, whatever you allocate, how large you have, that doesn't matter how large you allocate. It's also movable. I can move you when needed, right? So that's the most ideal situation. And then it's movable, right? You only request the 4K page, base page. Yes, it's very small, but it's not the worst because I still can move this 4K page when needed, so that I can make space for other compound allocations, right? Then the next one in this list is a movable compound, right? And then the last one is movable. Because why? Because in the worst case scenario, you can this type of allocation can spread out over the entire memory. Let's say you allocate a bunch of 4K unmovable, you make a bunch of unmovable 4K allocations. The worst case scenario is that you can spread those 4K unmovable pages all over the place and make every page block unmovable, right? So also there are runtime hints, which are we might not have the time to discuss, but basically this lifetime and hotness and coldness. But because we cannot, we might be able to, by doing sampling, we might be able to get some FDO data, feedback optimization data, but mostly the hints are runtime. It's not, we cannot really decide it without statistically sampling, right? So also with user space, so how do we really leverage this new economy? I just mentioned the opposite of what we currently have. We still we would need to make actually some. It's not 100% transparent, right? We may need some. User space might need to make some changes to also make this optimization better, right? So for example, I'll give an example here. So let's say we have two tasks running, right? One is high priority, the other is low priority, right? So right now, one allocates a bunch of 4K pages, the other trying to allocate a bunch of THPs, but it cannot because the first one actually fragmented the memory or made the THP allocation harder. So we need to, but the first task is also a low priority task. So that actually causes a priority inversion problem. So how do we fix this? We definitely need something from user space, right? Because without additional information from user space, we don't know the first task is low priority, the second one is high priority. So partitioning. So the idea is just like the image I included here to illustrate the idea. So we want to segregate the 4K partition and the THP partition so that we can have guaranteed THP coverage, right? Because without partitioning, we would only be best effort. We cannot provide guaranteed THP coverage. So of course, when you partition, if you say most none of the cars are coupled, right? We would have empty couple lane. So that means it will reduce the utilization, right? So here I also have a table to show the difference here. So again, this is completely the opposite of the existing scheme. So Now we have partition, right? But then we how do we exactly partition the memory? So we need to figure out how to do it, right? Of course, again, it cannot be 100% transparent. We would need something like min max, which are similar to memory usage min max, right? What does this mean? In addition to charging memory usage, we also actually charge physical contiguity. That means we see THPs as kind of a resource, right? I can quickly touch on what we actually do at Google. So at Google, we're not only concerned with memory usage, we monitor fragmentation. That means we also concerned with physical contiguity. We also monitor memory bandwidth or try to allocate the memory bandwidth, right? We also monitor cache, CPU cache. So that's more things we do because only worry about the usage in a multi-tenant system is not enough. You know, low priority job can use more THPs, low priority job can use more memory bandwidth, or low priority job can use more cache, right? This would all cause priority inversion. Questions on this one? Awesome. So next one, auto resizing and ohm kills. So to do all this, we also need to
Hang on a second. Sorry, we do have a question.
So this partitioning, is it through separate zones?
We are not there yet. Yes. And we're not there yet. Because that'll be the second topic, policy zones. We'll be there really soon. Because this is very general. How do we exactly implement this is like open to discussions. Right? You can, of course, I personally prefer zones. You can try to use page blocks. You can try to use other stuff to implement, right? The basic idea is like this area or this bunch of regions are for this purpose, and that bunch of smaller regions or that bunch of areas, that big area is for a different purpose. That's the whole idea. Okay. So also auto resizing and the ohm kills. So now we see, we prefer THPs and we see 4K allocation as second class citizen. So that means if you don't have enough 4K pages to fulfill the request, allocation request, you would have to make a decision whether you try to resize in zones or you try to ohm kill, right? That's only two obvious paths to go down. Of course, you can thrash, you can crash, right? But that's undesirable. So if you resize, right? If you make the THP zone smaller, or sorry, I should call it zone. I should call it partition. THP partition smaller, right? Then that means you might not be able to make it larger later, right? Because why? Because once you use it as a to allocate mobile allocations, right? You might not be able to move those over mobile allocations. Of course, you could ohm kill. Because why? Because as I said, 4K allocations are legacy, just like a device trying to allocate from DMA zone, right? And yeah, if it fails, it fails, right?
Can you hear me?
Yes.
I'm trying to get my head around what you mean by 4K allocations are legacy. I mean, if a driver needs 4K of memory, are you saying like, no, you should allocate 2 meg? I mean, that is just wasteful, right? There is no benefit to allocating more memory than you need just to not be considered legacy. Yeah, I'm trying to understand this.
No, it's not about driver. It's mostly about user memory.
Well, again, the user-based application will allocate as much memory as it needs, right? If it needs 100 megs, it'll allocate 100 megs, and then hopefully it'll get THPs. Again, are you saying that user space should allocate more memory than they need just to get THPs?
So if user space tries to get 100 meg, right? I can give you 100 meg of 4K pages. No THPs at all. And on the other hand, okay, two extremes. On the other hand, I can give you 100 meg of THPs, not 4K pages at all. Right now, it's like the best effort. When you set THPs to always, right? Right now, it's best effort. I'll try to give you as many as THPs as possible, but the worst case scenario is like you get 0 THPs. But now I'm saying we should do the opposite. I'll try to give you as many THPs.
Yeah. What are you asking the application to do differently?
Nothing.
So then what
But,
does it mean
you
to
know,
look at 4K as legacy? Like,
that means when we design the system, we think, okay, if you try to right now, as long as let me put it this way, as long as you have free memory, right? And right now you always can get 4K. This makes sense, right? There's free memory, and you allocate 4K, you always can get it, right? And what I'm saying is this making legacy means, oh, there's free memory, but actually it's not for 4K. You only, that free memory is reserved for THPs only.
I mean, if your user space application only needs 4K of memory, are you telling me I actually have to allocate more memory than I need so that my allocation will succeed?
No, what do you mean by user space only need 4K memory? You mean user space? Okay, this depends on how you set a THP. If you set THP to always, this user space this allocation can be backed by THP, right? You will get a THP instead of 4K. If you're trying to allocate 4K, and let's say because
benefit
you
of backing that allocation with the THP. You only actually benefit if you're allocating a large amount of memory and you're optimizing your TLB performance, then it makes sense to use THPs, right?
It depends, because you have THP you have your own THP settings, right? You can set it to different way. You can disable THP. Of course, in this case, we will not be able to reap the benefit from this THP partition, right? But if you set THP to always, right now it's like if you have free memory, you're not guaranteed to get THP, but you are guaranteed to get 4K. So there is a priority here, right? Which one is like when you have free memory? What this free memory would be? Would be a 4K page? Would be 512 4K pages, or would be a 2 meg THP?
Whoever needs the memory, right? If an application only needs 4K, it should split that THP, and you should split that huge entry in the buddy list, and the caller should get their 4K.
If I cannot give you, if your allocation is not aligned, right? I cannot give you THP in the first place. I would try to give you 4K, right? But if I have free memory, I'm not gonna split those free memory into 512 4Ks. I would try to reclaim some memory from the 4K partition, right? So if you say, okay,
let me ask the question differently. The thing is that it sounds like we have like a two-class system now. We have the very bad 4 kilobyte, and everything else is very good. Do you envision that we will run, and I think I asked that question Pauline at some point on the mailing list, but I never got a reply. Do you envision that the more we move towards like using, I don't know, 16 kilobytes, 32 kilobytes, that will run into the same issue again, that will say, well, like 16K is bad? Like, what I'm trying to say is there like a clear distinction what is really bad and everything else is good, or do you think we might run into similar issues again once we have more larger but still small folios?
You mean really bad is in terms of the granularity, or in terms of coverage?
Whatever you try to improve, let me phrase it this way. I mean, like, of course, like if you allocate 1 megabyte, you can back it by 4 kilobyte, or you can back it by 16 kilobyte, or whatever you use. But is there then a clear distinction that 4 kilobyte is bad and 16 kilobyte is good? if you get what I mean, because it will all go to the other like special area.
Yes. So here's the observation from our fleet, right? Because basically, how do we decide which page size to use? That's a very simple question here. I think I should have touched on this part before. So basically, we need to have for every workload or for all workload we have, there's a median page size. This makes sense, right?
Like 3 page sizes. You don't go all the way from, I don't know, 4, 16, 32, 64, 128, all of the way. Do you specialize only on 2 or 3?
No, you can actually see this because here's how it works. You can look at the page tables, right, to see, okay, this region actually can be backed by 4K, 8 4K, right, and or 8K or 216K or 132K, right? By make a histogram, you see, okay, actually this much memory can be backed by this page size, and this page size is the median page size.
Right, and I think for the 32 kilobytes, it's easy, but assume like you have 1 megabyte. Like there are so many combinations, and I'm asking like, is it fair towards 4 kilobyte pages to say that they are the bad guys, but 16 kilobytes are the good guys, if you get what I mean?
I think I got what I mean. I think if you look at distribution, right, probably it's like a bell curve. So 4K is definitely on the left end. Because we cannot make smaller page allocations, right? This makes sense, right? And for server workload, why is it bell curve? Because you have so much memory. I don't. Go ahead.
No comment.
Okay. So the median will be larger, definitely larger than 4K. But how large it is, that's the question. So that's why I mentioned how we actually sampled our workload to see the median page size there. Because you don't really need the MTGP support, or you don't really need to turn on MTGP to get this information. You could just look at a page table, right, and say how is it possible to back this water space with a larger page size?
Sorry, this is John Hubbard. I had a question. It seems like if you've got kind of a hard-edged rule where you are resistant to splitting a larger page, it sounds like you're moving toward huge. It sounds like it wants to be huge TLBFS. Just kind of tossing it out there. I've kind of warmed to huge TLBFS over the last year as I've watched applications move between that and THP, and it's pretty clear that if you really need pages of a certain size that huge TLBFS works well, you're willing to make that trade-off and say, I've got a distinct carve-out. That's really what I need. It's super important. Whereas if you want the flexibility of being able to get the 4K pages if you really want them, because you've got zillions of small things, and in that case, you don't want to resist splitting the huge pages. So I'm having a hard time mentally placing where your feature fits in here and why you wouldn't just stick with the existing division. Try to make THPs flexible and responsive to the right amount of fragmentation pressure, the right amount of how hard you should defragment, and then just let huge BFS run.
Yeah, so we're out of time. So very good question. So that's actually going to be covered in the second part. So policy zones. So what I'm trying to do with this THP example, what I'm trying to do is to make this more generalized. With the policy zones, you not only you can actually back huge TLB, you actually can back THP. So basically, the THPs and huge TLB, they converge, right? Why do we want to use huge TLB? Because we want very specialized, very guaranteed coverage, right? But that's a special case because it has its own pool, right? It has huge TLB cannot be reclaimed. right? If you want to read around reclaim, you cannot do this, right? Also, a lot of the special treatment we do that's different from what the core MM does, right? So actually, the design goal here in the short term is like we not only can infer what exactly you want to do automatically, right? We also can in the long term, at least here, we want to eliminate the need of specialized pool. That includes CMA and HTLB. We also want to deprecate or eliminate the DMA and DMA30 zone because that can be done differently instead of using zones, right? Because that's hardware specific thing, which I don't think that's as important as the software policies. I know it's still very big, but I hope you can just roughly get the idea what I'm trying to do here. What do you think, John?
Well, okay, so it's gone 6:30, and the AV team are going to have to start tearing down the room. So, do you want to go like another 2 minutes? Is there anything else you need to say?
Yeah. So I just want to say the use cases here. The community at Opal, I think, talk about this. The deploy this. Also at Google, we also trying to leverage this to do HVAO for THPs, not for HTLB, right? And also we also plan to support 1 GBT HTTPs. It's not 100% transparent. You still have to add some new Madvise new Madvise calls, but I think it's doable. Also, we can use separate HTML page sizes for CPU and device, right? Because you have a zone, you can say this zone only supports this base page size, and then this zone can be shared. This CPU zone, memory zone, can be shared with device. For example, GPU. So also I have a comparison table why we're trying to use zone, not page block, not new page block types. So yeah, 2 minutes. More questions here?
All right, thanks for the presentation. Appreciate it. Thanks.
Half went better.